Hey, Cody, sorry about missing you there.
Oh, it's all right. My internet died for a little bit in there anyway, so yeah.
Yeah.
So yeah, if I disappear in this, it'll just my internet's down, so it'll take me a second to get onto my laptop. Well, how was everyone's weekend? Seeing a bunch of mouths move, but I hear nothing. It's a wonderful time.
How's your weekend?
It was all right. By the way, I've been meaning to say this to you, Alejandro. At the end of our last semester, I saw your email and thought I responded to it. And then I realized at the start of this semester, when I saw your name again, that I didn't respond to it. And then life caught me. But so I just want to let you know, I didn't mean to ignore you. I honestly thought I responded to you.
That's all good, bro. I know stuff comes up.
All right.
All right, everyone. Good afternoon. Welcome back. So the test results were good. I sent an email out about that already. We had 8 A's, 6 B's, no C's, 2 D's, 1 F. Here are the grades from highest to lowest on the exam. So you can maybe from that tell where you land. The thing that I thought was really good, the class average was an 85, but the standard deviation was 12, which I always keep track of the standard deviation because that just tells you how far apart students are. And normally in most classes that I've taught, the standard deviation is somewhere around 15. I don't think I've ever seen anything below 10. So 12 is really a lower standard deviation, which is good. That means that the majority of the class, you're all kind of at the same place in terms of what you did on the exams. And that makes it a lot easier for me to teach to a class that is clumped together as opposed to having huge disparity between the students. So that's good news. Any questions over the exam or concerns or anything else before we start getting into today's stuff? We're happy. All right, well, today we're going to do more related rates. We had just started talking about that at the end of last time. Remember the things that were not on the test, right? I did not test you on implicit differentiation. I did not test you on chain rule, right? No chain rule on the test, no implicit differentiation, and no related rates. So there are two major sections that we did not cover that'll be on the next test. And related rates, we just started talking about word problems and how we can use implicit differentiation to solve some rather strange types of word problems. So we're going to cover related rates for most of the class, and then we'll start talking about derivatives of exponential and logarithmic functions. If you just think for a second, we have steered clear of exponential and log functions. We have talked about polynomials, we've talked about rational functions, we've talked about the trig functions and what their derivatives are. But we have steered clear of the exponential and log functions because we just have not talked about what the derivatives of those are yet. So we'll talk about that at the end of class, or probably the last third of class we'll do that. I want to try and do as many related rate problems as possible because no matter how many I do, you can do 100 related rate problems and then the next one will be something you haven't seen. So really, I'm just going to try and expose you to some of the classic related rate problems. And then towards the end, we're going to do 2 related rate problems that I've never done before. that I prepared as far as the setup for it's in place, but I have not actually done the problem. So it'll be interesting to go through those, and you know, my first time through, your first time through, we'll see how it goes. Okay, so related rates. Let me get to the notes here. Oh, wrong one. So related rates, what I told you last time is that there's kind of a systematic approach to it. You can do these steps, but there's no like step 1, step 2, step 3. It's more like all the steps you have to kind of be thinking through them all simultaneously. And I included a worksheet, or I told you about a worksheet on our website that you can use to help you on these problems. So I'm going to be using that worksheet as we do some problems here. So we did a circle problem. I don't know if you remember this from last time. We had a circle that its radius was growing at a constant rate. And then we were trying to figure out how fast how fast the area was growing at a specific instant in time. What I'm going to do now is I'm going to change the problem. We're still going to have an expanding circle, okay? So I want you to watch this happen, okay? Watch this animation and notice that the thing that's changing at a constant rate is not the radius, it's the actual area, okay? So pay attention, just let me slow down a little bit. Pay attention to the area. It's, I'll slow it so we can count. There we go, 40, 41, let me go a little slower. 45, 46, 47, 48, 49, 50, 51, 52, 53. So the area is growing at a constant rate. The question is, you know, how is that impacting the rate of change of the radius? So if I drag this back to the beginning, watch in the beginning how fast the radius grows. 1. It got to 1 real fast. Now it's taking a long time to get to 2. 2, it finally got to 2. And now it's going to take even longer to get to 3. Still not there. It finally got to 3. Now to get to 4, it's going to take even longer. So what's happening here is we're adding. Take a picture of this real quick. We have this circle that's growing, and as it grows, we're adding the same amount of area to it, okay? It's constantly adding the same amount of area. But because the circle is getting bigger, that means that the radius is not going to grow as fast as you go out and get bigger and bigger and bigger. Does that make sense or not? I need like a nod, yes or no, because there's a major difference between this and the radius growing at a constant rate. Okay, I'm going to assume you're okay with that. So the question here is this. Here it is. I'm going to take this over to our notes and let's work this out.
Just thoughts that just pop into my head. The problem always dictate what is constantly increasing, right? We're not gonna have to try to figure that out. They're not gonna just give us like an equation and say, okay, what's increasing constantly?
Yeah, they're going to always give you. They're going to give you some rate. Okay, they're going to have to give you some rate. Can I make this smaller? Come on. There we go.
Quick question about this sheet that you have to help us, the related rates worksheet. Will we be able to like just utilize this on the test?
Yes, I'm okay with you using this on the test, but you obviously would have to make a copy of it before, you know, several copies of it before the test.
Yeah. Okay.
Yeah.
And then if we did end up using these, we'd have to have a new one for every problem. And then I'm assuming we'd have to scan this in as part of Scratch.
Yeah, if all your work is here, then I need to see this.
Okay.
Okay, here we go. So step back. if you took anything away from the last class, it was that if somebody gives you, if you have any equation out there in the world, okay, any equation that relates variables together, we can always differentiate that equation with respect to anything we want. And what that will do is it will make a new equation that connects the rate of change of those variables together. It relates the rates, which is why this is called related rates. And remember that a rate is a change and a change is a derivative, right? So let's read through this. If the area of a circle is increasing at a constant rate, okay? So the area of a circle is increasing at a constant rate of 1/5 square foot per second. They are giving us a derivative here, aren't they? They're telling us how fast something is changing, specifically the area of a circle. Okay, so that is this right here. We should be thinking this is the derivative of something, right? This is the derivative. Okay, the question is how fast, right? How fast? So they want to know the derivative of something because speed is a derivative. How fast is what? The radius increasing. And then they give us a specific instant when they want us to look at exactly the moment that the area is 5 square feet. So they give us a derivative. They ask us for a derivative at a specific moment in time when the area is 5 square feet. Understand? Let's draw some pictures. We have 2 pictures to draw. The first picture is the picture of just a generic, I'm sorry, not generic, the circle that we're talking about at the instant in time that we're talking. So at the instant in time, we're talking about when well, what do they tell us? At the instant in time,
when our radius is going to be 5 foot squared.
the radius?
Yeah, the radius.
The area
Or
is.
the area, sorry.
The
yeah.
area. So at the exact moment in time, what I can tell you is that the area is 5 square feet, right? At that exact moment. Now, let me ask you something. If I tell you that the area of a circle is 5, can you give me the radius?
Yeah.
Yeah, because you have a formula that you are aware of. Area is pi r squared. So if I tell you that A is 5, you could solve for R, couldn't you? So even though we don't know what R is, sorry. Oh, shh. Okay. So even though we don't know what R is, it's not given to us, we would be able to solve for R, right? If we needed to, we could solve for R. So I'm going to put here R right now is unknown, okay? But I'm going to put a check mark next to it because that just tells me like I could get it if I need it, okay? Now, the general picture is another picture of a circle, but now we have to imagine that this circle is in motion. It's changing, it's growing. It's growing because the problem says that the surface area is growing, so it's getting bigger and bigger and bigger. So when it's growing, the radius is just R. We don't know what it is. It's just something, some arbitrary point in time. And of course, the area of this would be, well, something, but we know it would be pi times the radius squared, right? So I'm just kind of jotting down ideas here. Now, while I'm doing this, I'm also thinking about what I'm given and what I want. So what were we given in the problem? We're giving some information about some things. So does someone want to tell me what the 1/5 square foot per second represents?
Derivative of area?
It's the change in area, right? It's the derivative of area with respect to what?
Time.
Time. We know that because seconds is measured in time, right? As a measurement of time. Square feet is a measurement of area. So we know that we are given that the change in area with respect to time is 5 square feet per second. Now, what do we want? Somebody tell me what you want in terms of, go ahead.
What is it, 1/5 or 5?
Oh, yeah, it's 1/5. I don't know why I wrote 5. Sorry, I know I wrote 5 because the 5 from right there, but I was just not thinking. Sorry, 1/5. Okay, so what do we want? So it says how fast, right? We want to know the derivative of what?
Radius.
The radius with respect to time, right? So we want to know what dr dt is, right? We would like to know what that is at the exact moment that what's happening. At what exact moment?
That
At our
area is
area.
5.
The
Right.
area is 5. So I'm going to put here at the moment that A equals 5 square feet. And that pretty much encompasses all the information I'm given, right? I know how fast the area is changing with respect to time. I want to know how fast the radius is changing with respect to time. And I want to know that at exactly the moment that A is 5. Now, something, again, I know you were all studying for the test and everything, and maybe you've forgotten this, but one of the most important parts of these problems is that when you're talking about the moment in time, this A equal 5, you are not allowed to fix or put 5 into anything until after you've differentiated. Because if you put it in before you differentiate, then you're freezing the picture, and then your derivative will always be 0 because nothing's in motion. So when we go to set up our equation, which is the next thing I'm going to look for here, this equation, all I'm trying to do is find any equation that exists out there that relates that variable and that variable together. The area of a circle to the radius, any equation, but obviously we have it, right? We've written it down twice already. Area is pi r squared. So I'm going to write that equation down. And now I'm going to differentiate this equation with respect to time. So when I differentiate the left side, what is the derivative of A with respect to t?
dA over dt.
dA dt. Okay, on the right side, I have pi. Pi is a
Constant.
constant, so it's just going to come for the ride. Now, r squared is a variable expression, so I have to first apply the power rule to r. But then chain rule says I have to now take derivative of the base, which was the r, with respect to time, which would give me the dr dt. And this is the equation that I want to mess with now. Okay, I'm put it here in my scratch work spot here. So this new equation has everything that I'm happy to see, because dA dt, I know that, right? dA dt is 1/5. dr dt, I'm put a check mark above that because that's what I'm trying to find. And the r here, that's the one piece that I'm not sure of. I don't know what r is directly. I know what a is, right? But I don't know what r is. But we said in the very beginning that when we fix everything, then we could find r, right? So I'm going to have to do that. And I'm allowed to fix everything now because I've already differentiated. So all the related rates have been established. So to figure out what r is, I'm going to come back up here and I'm going to say, well, I'll do it down here. I'm going to say, okay, wait on that. I know that area is pi r squared, but I know that the area is 5. And if I divide by pi, I get r squared. And if I take the square root, I get what r is. And I don't do plus or minus on r because r is a radius, so it's got to be positive. So I'm not even going to think about the negative answer. But that's what r is, okay? So now I can go back to this. And I know dA dt is 1/5, sorry, 1/5 equals pi times the square root of 5, 2 times, sorry, the square root of 5 over the square root of pi. I broke this up into two fractions, root pi, or root 5 over root pi, and then times dr dt. Now, we could get the exact answer or we could get the approximate answer. I'm going to just do the approximate. I'm just going to get on my calculator and figure out. Let me just figure out what all this is. Okay.
My internet DC, but why is the pi pulled out? Why is it not like, is it just pulled out because it's being treated as a constant, or?
Where, when we differentiated?
Yeah, when we differentiated.
Yeah, because it's a constant attached to a function, it comes for the ride.
Okay,
And then you have to just differentiate r squared, which is this piece.
right. Yeah.
All right, square root of 5 divided by square root of pi. Okay, on the right-hand side, 1/5 equals, I'm getting like 7.926 or 7.927 is dr dt. Let's make sure that looks okay, yeah. And then I'll just divide both sides. 1/5 is 0.2. So I'll take 0.2 and divide it by the right-hand side. And I get 0.0252 is approximately equal to dr dt. Now, the last thing we need to do, and this is important, is to put the units of this measurement here. So dr dt is the change in radius over time. Okay, how would you measure the radius if I asked you to measure the radius of this circle? What are the units we're using in this problem?
Feet.
Feet,
Feet
right?
squared.
So the radius would be a measurement of feet, and then time in this problem is measured in
Seconds.
Seconds.
seconds. So this would be feet per second. Okay, let's recap. That's our solution. 0.0252 feet per second. So to recap, we have a circle that's growing so that its area is increasing at a constant rate of 1/5 square feet per second, or 0.2 square feet per second. At exactly the moment that the area of the circle is 5 square feet, at that exact moment in time, I can tell you that the radius is increasing at 0.0252 feet per second. Questions?
Now, that would not be the second derivative, would it? That would be just things plugged in.
That's just,
Like,
yeah,
that
it's
was-
just the first derivative.
So then we'd have to take the derivative of that to get the speed at that point.
No, that is the speed. That is the speed, because it is a derivative. This is dr dt, right? So that is the rate of change of r with respect to time. So that is a speed already.
Was it the second derivative, was that velocity then, or? I don't remember.
Second derivative is acceleration.
Acceleration, okay.
But hold on, because you can't take the derivative of this to get acceleration, because this is a constant.
Right. I was putting
But
pieces
what you
together.
could do though, is you could take the derivative of this again
Yeah,
with respect to time, and that would generate your second derivative.
okay.
But it'd be very complicated because you'd have derivatives of things that are already derivatives. So you would have
Yeah.
second derivative. Yeah, it would get complicated. Okay, let's move on to another problem. Like I said, I'm going to try and do as many as I can. Oh, you know what? Let me just copy that. Copy. Paste. There we go. All right, next problem. All right. This time we're going to do a different problem that has to do with a sphere instead of a circle. If the radius of a sphere is increasing at a constant rate of 2 feet per second, how fast is its volume increasing when the volume is 36 pi cubic feet? I'll bring this over in a second. Let's just take a picture or look at a picture of what's happening. We have a sphere. the radius is growing at a constant rate. The radius is changing. How does the volume change? So let me start this over. Look at the radius first. The radius is going up by a constant rate, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It's constant. But look at the volume. It's going to start growing really fast. 4, 5, 6, 7, 8, 9, 10, 11. Can y'all tell that the volume is increasing in speed here?
Yeah, it's
growing
kind of
much
exponentially starting to
faster.
pick up.
Faster and faster and faster as the radius grows at a constant rate. I didn't hear you, Cody.
I was just saying it's almost exponential. It's almost like exponential in nature. It slowly goes up. It's increasing more and more.
That would be an interesting question. Is that exponential or not? We would have to see. We have to look at our relationship.
Yeah.
I mean, I know when you watch the news and stuff, people throw the word exponentially out there a lot. In math,
Yeah.
we understand that exponential is a specific type of growth, right? It's a number raised to x.
Yeah.
A lot of people will say like any fast growth is exponential, but that's not necessarily the case. Okay, let's look at this. If the radius of a sphere is increasing at a constant rate, okay, they tell us we're given that the radius, right, of a sphere is increasing at a constant rate. That's a derivative. There it is. That right there is a derivative. Can somebody tell me what that is the derivative of? Like, what is this the rate of change of?
It's radius over time. Yes.
Yeah, radius over time, right? This is telling us the rate at which the radius changes over time. So right now I could just write here dr dt. Make this a little smaller. Dr dt is 2 feet per second. Okay. How fast? Oh, they want to know how fast. They want to know derivative. The derivative of what? Volume, right? They want to know how fast volume is changing with respect to time. And they want to know it at exactly that moment. So what do we want?
dv dt.
Yeah.
ddt, right? And we want it at exactly the moment what?
36.
Moment that we're 36 pi feet cubed.
Okay, yes, but what is that? What is 36 pi?
Volume. A constant.
The volume, right? The volume.
Yeah, volume.
At the moment, the volume is 36 pi. You see, I'm doing this problem a little different. I'm not drawing a picture. Just to show you, you don't have to do these in a particular order. So let me draw my sphere at the exact moment. The way that I draw a sphere is I draw a circle, low, and then I just draw like this weird sort of ellipse looking thing in the middle of it like that. Kind of makes it look three-dimensional. I know that this sphere is going to have some radius. And I know at the instant in time we're talking about, I know that the volume is given to me to be 36 pi cubic feet. In general, I have a sphere that's growing. The radius is changing and the volume is changing, right? The volume is something, right? But it depends on the radius. So in the general picture, you cannot fix anything. Have I made that clear? You cannot fix anything. So at this point, can you connect the radius and volume together for a sphere? Is there an equation out there that connects the volume and radius of the sphere together?
4/3 pi r cubed.
4/3 pi r cubed. So this on our formula sheets, we are given this one. For a sphere, the volume is 4/3 pi r cubed. So we can say, all right, well, then the volume we know is 4/3 pi r cubed. And that's great because we have V and R in here, and that's what we are interested in finding out about, the related rates. So we're going to just differentiate this with respect to time. We get dv dt on the left side. On the right side, 4/3 pi is all a constant, right? That's all a constant. But you still have to take derivative of r cubed. So that'll be times 3r squared, that's power rule, times dr dt, that's chain rule. Any questions on that derivative? Time to do some work with this. dv dt, I'm going to put a check mark above it because that's what I'm looking for. So I'm happy to see it. dr dt, I'm okay with that because I'm given that that's 2, right? The thing I don't have right now is this r, right? I don't have that. I don't have it directly, but can I get it?
Yes, you can just set 4/3 pi r cubed equal to the 36 pi and then solve for it.
Exactly, we can use that. I'm gonna do it right here because it'll just fit better here. I know that the volume is 36 pi, so I know that 4/3 pi r cubed equals 36 pi, like that. So I can solve for r. I can divide both sides by pi, that'll get rid of the pi's. And then I can multiply both sides by 3/4. That'll get rid of this over here. We'll just be left with r cubed equals, let's see, what is that, 9? I think that's 27, which means r is 3, because the cube root of 27 is 3. So at the exact moment that we're talking about, when the volume is 36 pi, that means that the radius has to be 3. So now I know what r is. Any questions? I'm almost done. So dv dt must equal 4/3 pi times 3 times 3 squared times dr dt. Oh, we know dr dt is 2. So that's 2. The radius we said was 3. And dv dt is what we're solving for. Any questions on where any of that came from? No? I'm going to cancel those 3's. Could have done that a long time ago. dv dt, change in volume with respect to time is, let's see, that's 9. And then 9 times 4 is 36, and then times 2 is 72 pi. I think I'm getting 72 pi here. That's the exact answer. If you wanted to know it as a decimal, you do 72 times about, pi 3.1415. You get approximately 226.195. What though? What's our unit?
Feet.
So we want to look at V over T. So volume would be measured in what in this problem? What's volume measured?
Feet cubed.
Cubic foot or feet cubed. So it'll be feet cubed. Let me put my answer. 72 pi feet cubed per, what's our measurement of time? Second. And this is, just so we're clear, this is dv dt. All right, so we have a sphere, right? It's growing. Its radius is changing at a constant rate of 2 feet per second. At exactly the moment, the volume of that sphere is 36 pi cubic feet. At that exact moment, the volume is changing at a rate of 72 pi cubic feet per second. All of the problems I've done so far have been very, very similar to one another. Circles, spheres. We need to do something else, right? Not everything's going to be a circle and a sphere. This is just to get the flavor of kind of how we approach things. You all ready for something different? Yes? Of course you are. Okay, this is a classic problem. A plane is flying horizontally at an altitude of 2 miles and a speed of 600 miles per hour. The plane is headed directly over a ground-based radar station. At the moment the plane is 6 miles from the radar station, how fast is the distance between them changing? So I'm gonna leave that up there. I'm gonna show you an animation of what's happening here. Try to make this a little bigger so you can see it. Okay, so the black dot represents a radar station on the ground. The red dot represents a plane. Okay, so you've got this plane that's flying overhead. So let's say here's the radar station, here's the plane. The plane is 2 miles off the ground and it's flying horizontally. Oh, by the way, we're not going to take the curvature of the Earth into account here. Of course, that in the real world we'd have to, but here we're just, you know, baby steps. We're just going to act like it's flat Earth, I guess, for today. All right.
Oh, boy.
I know we won't go there, but yeah. All right. So this is just, again, to get the general idea of things down. So here's this plane flying overhead. Okay. Slow it down. And if you were to connect the plane to the radar station with a straight line, just think of it as like a rope, okay? Then what we want to know is like how fast that rope is changing, that distance between the plane and the radar station at a specific instant in time. So we're talking about a specific instant when at the moment the plane is 6 miles from the radar station. Let me show you where that is. Right there. At this particular moment, this distance is 6. At that moment, I want to know exactly how fast this distance is changing. Do y'all understand that? Now, when the plane goes past the radar station and goes this way, isn't there a point over here will also be 6?
Yeah.
But now that red line would be growing instead of shrinking, wouldn't it?
Right.
Okay. It actually doesn't matter which situation we look at. We can look at it as the plane is coming towards the radar station or the other side where it's moving away. It's completely up to us. But if you read the problem, it makes it sound like the plane is approaching the radar station, and we want to know at exactly the instant that it's 6 miles away, 6 mile distance from here to here. At that moment is when we're interested, right? So one of the big questions you have to ask yourself is, if I didn't give you this picture, could you have come up with that geometry on your own? Could you see all this together? That's going to be part of the challenge for you, all right? So let's start taking this problem over to the sheet and seeing if we can't figure it out. Would y'all like me to give you a few minutes to see if y'all can't figure it out? Y'all want to do like breakout rooms, or why don't I just, we'll leave everyone in here, but let's see if you can't fill out at least part of this, at least some of this here. Make this a little bit smaller. Oh, shoot. I don't know what I just did. There we go. Okay. Let's take 5 minutes. I'm going to just see how much of this you can put together. All right. See what you can do. And then I'll open it up to the floor in 5 minutes and see what people have come up with. We're just going to go one more minute. I'm not expecting that you solved it. I just want to see how much of it you can get started. Okay, so I'm thinking about what would be most constructive here. So how about we do this? Is some brave soul willing to say that they're completely lost and not quite sure how to start? Is there anyone just who's like,
I
have
got
no
the
idea.
equation.
I'm
Yes.
lost.
Yeah, I'm lost too.
Justin, okay, so I saw Justin unmute himself and raise his hand. So let's go with Justin. Let's start with the instant in time, Justin. All right.
Mhm.
Did you draw anything for the instant in time, or do you have a visual idea of what it looks like?
Yes, I did.
Ground, radar station,
Mm-hmm.
plane. What can you tell me? For sure is,
They are 6 miles apart. And
okay,
the
so
plane is
you
2
know
miles
that this one is 6. What else do you know?
The plane is 2 miles in the air.
2 miles high. Okay, so I'm not drawing this to scale, okay, but this is 2, and that would be a right triangle. Yes?
Yes,
Okay,
I agree.
I agree completely. All right, let's go to the general picture. You have a radar station,
Mhm.
you have the plane, but now, Justin, you actually don't know the distance between them, do you? Because the plane's moving.
That is true.
So since you don't know what it is, you have the freedom to call it whatever you want, but it has to be a variable. So what would you like to call that red line?
I'm gonna go with X.
You want to go with X? Okay,
Mhm.
I'll go with X. So that's X. So everyone agrees that as the plane flies horizontally, the plane is flying along this horizontal dotted line, that X is changing, isn't it?
Yes.
Okay. Now, on this picture, Justin, is this still 2?
Yes.
Okay, that's 2, that's fixed. Okay, I agree. Now, I'm good with that so far, okay? Maybe we can talk about what we're given. Okay, so when you're given something, Justin, in the problem, you're going to be given something that is a derivative, a rate of change. So do you
That'd be
see anywhere in this
600 miles
problem?
per hour.
The what?
Would that be 600 miles per hour?
600 miles per hour, exactly. This right here is the derivative. This is the derivative of something, right? That's the derivative. That's the rate at which something is changing, right?
Mm-hmm.
So Justin, in your picture, the way we have it drawn right now, do we have a place to put the 600? Other than the fact that there is a plane here. We know this is a plane, thank you. I know it's really a good looking plane. We know that that plane is moving at 600 miles per hour, right?
Yes.
Is that how fast X is changing?
No.
No, it's definitely not. This never changes, right?
Mm-hmm.
All right, so let me help you with this, Justin. Do you agree that if you were to put a dot straight below the plane, that if the plane is moving at 600 miles per hour, then this dot is moving towards the ground at 600 miles per hour also?
Yes.
Okay, now then why don't we call this side something? What do you want to call it? Give it a variable.
R.
R, okay, so you called it R. This is R. Okay,
Okay.
so does everyone agree that the plane moving across the horizontally is equivalent to R changing? Right?
Yep.
R shrinks at the same rate that the plane is moving. So the change in R with respect to time, Justin, is also the same as the change in the plane's, the plane's speed is actually the speed of that point moving. Do you all see that?
Yes.
Okay, so what are we given then, Justin, in terms of our picture now?
Is it
We're given the rate at what?
DRDT.
Yeah, we are given DRDT. Now this is tricky, Justin, this is tricky. What is that rate of change?
I want to say, is it 600 miles per hour? Because that's the first thing. that comes
Yes.
to my head.
Yes, I mean, yeah, this is kind of a tricky question. I'm loading it for you here. It is 600, but is it growing or shrinking, Justin? Is R getting bigger or
Oh.
smaller?
It's getting smaller. So,
So
would it be
that
negative?
means the rate of change has to be negative
Okay.
because it's shrinking as opposed to growing. So we're going to put negative 600 miles per hour. Is that clear to everyone? The rate
Yeah.
at which R is changing is negative because it's shrinking. Good. Is this making more sense, Justin?
Yeah, it is.
One of the things that we had to do in this problem that we had not run into before was create this variable R from the geometry of the problem. It wasn't as simple as area equals pi r squared or volume equals 4/3 pi r cubed. We didn't have these nice formulas in place. We had to actually generate those ourselves.
Question, sir.
Okay, yes, what?
So since it's going to be the exact same value at 6 miles on the other side as it's increasing, do you have to put the negative there? Like, I mean, I imagine maybe in certain instances you might, but
No, you would not if it was a scenario where the plane had already passed over and was moving away from the radar station. Just we have to be consistent with everything. Like if we're going to say it's this, we have to make sure that anything that grows is positive, anything that shrinks is negative. It's on the other side, anything that grows is positive, anything that shrinks is negative. We should get the same answer, it's just a different signs. Because do you all agree X is shrinking? In our picture, X is shrinking, right?
right.
So our answer should be negative. Whatever we get, our answer should be negative.
I didn't hear you. What?
Our answer will be negative because X is shrinking.
Right.
All right, we're going to stick with Justin. Justin, what do we want to know?
Dx dt, right?
Dx dt, good. So X is the distance between the plane and the radar station. We want to know what that is. At what moment in time, Justin, do we want to know that? At exactly
At
what?
x equals 6.
At exactly the moment that X equals 6 miles, right?
Yes.
That's it. Okay. Any questions on that? It's very important that you label this X equals 6 because it's not at R equals 6. It's at X equals 6. R is not the distance from the radar station to the plane. R is the distance from the radar station to like a projected shadow of the plane straight down. That's not what we're interested in. We're interested in this one. Okay, we're almost there, Justin. Justin, can you think of any equation that exists out there that somehow relates the X here to the R here? Anything. And you have to look at this general picture. Yeah, Pythagorean, right?
Mhm.
You have a right triangle. A squared plus B squared is C squared, right? A
Sure.
squared plus B squared is C squared. So tell me what that equation would look like for us, Justin.
2 squared plus r squared equals x squared. Right?
Yep. 2 squared plus R squared is X squared. Perfect. Now, think about this, everyone. I mean, that's a very basic equation. I hope you all agree, right? Right triangle, Pythagorean.
Mm.
But the key now, Justin, is to look at that and realize, you know what? You created a relationship between X and R, right? So if you differentiate it with respect to T, you know you're going to get a dx dt in there. You know you're going to get a dr dt in there because of chain rule. And those happen to be the things we're looking for, right? So everything's all right. Good job, Justin. We're going to move on. Who else was confused to start this out? Didn't know where to. Cruz, are you?
Yeah, that's the part that I'm having issues with is the implicit differentiation.
Okay, so with this, we're going to do we're going back and we're doing the derivative with respect to time on both sides of the equation. Okay, that's what we're going to do. So Cruz, we have addition here, right? And we're about to take a derivative, but we have addition, which means we can do them separately. So we can do the derivative with respect to t of 4 plus the derivative with respect to t of r squared. And that must equal the derivative with respect to t of x squared. That good, Cruz?
Mhm.
Okay, now, what is the derivative, Cruz, of 4? So what is the derivative of a constant?
0.
0 always, all right? So that's going to be 0, okay? Plus, now this is the part that I think is probably confusing. What is the derivative of r squared?
It would be.
Use your power
Well, r
rules
squared
first.
it's 2r.
2r, okay? But then chain rule says, all right, you've taken the 2, you've brought it out, you subtracted 1, but now you have to do chain rule, which means take the derivative of r, the base. Okay, so this is let me just show you an analogy of this. If I were to go back and I were to ask everyone in this class to take derivative of x squared plus x to the 7th power, chain rule says the 7 would come out first, then you do everything in there to the 6th, times, then you'd go inside and take derivative of that, which would give you 2x plus 1. Does that make sense, Cruz? Okay, we're doing the exact same thing here. The 2's coming out, we have 2r, but then we have to take derivative of r, but it's with respect to t, not with respect to r, so we don't get a 1 here. We get dr dt.
Yeah.
With that same idea, Cruz, what would we get on the other side?
This one we would get 2x times dx over dt.
Yes. And if I rewrite that up here, we have 2r dr dt equals 2x dx dt. Just got rid of the 0 out front. And now I'm going to just start looking at things, okay? I'm going to look at things here. What do we have? What do we not have? Let me see. Do we know, okay, what about r? Do we know r at the exact moment in time?
No.
We don't. Could we figure it out?
Yes.
Yes, because remember, Justin had said that this side over here is r, right? Justin said, we're going to call this side r. But in the instant, right now we can look at the instant. R is one side of a triangle where we have the other two. So we know the relationship r squared plus 4 equals 36, right? So a squared plus b squared equals c squared. If I do this, r squared equals 32, and take the square root, I know that r would be the square root of 32. So even though I didn't know this initially, because of the geometry over here, I actually do know what r is.
So-
dr dt, go ahead.
Since we took a square root, that would be like plus or minus the square root of 32, right? So then would we have to do two different equations for that, or? Well, I guess
Well, within the geometry of the problem, r must be positive.
Okay.
Because r is the distance from the ground to the shadow of the plane, the radar station to the shadow of the plane on the ground, right? So we're gonna it only makes sense to think of r as positive.
Fair enough, yeah.
So do y'all agree we know what dr dt is, right? That's given to us in the problem, -600, so I'm happy about that. Do we know x at the moment in time?
No.
Yeah, it's supposed to be 6.
Oh, yes, 6.
Right? Okay, so it's 6. And what about dx dt? Do we know dx dt?
We have to
Oh,
solve.
that's what we're looking for.
But that's what we're looking for, right? So we're happy. We have everything that is unaccounted for in the problem, we can account for it. So now it's just plug things in and chug out the answer. So 2 times the radius, root 32, times dr dt, which is -600, equals 2 times x, but x was 6, times dx dt. I'm gonna just get on my calculator and figure out the left-hand side. The left-hand side is negative 6788.23 equals 12 dx dt. And then I'll divide by 12. And I get negative 565.68 equals dx dt. Last step is to get the units. So x is the distance from the radar station to the plane, and distance in this problem was measured in what?
Miles.
Miles. And time in this problem was measured in what?
Hours.
Hours. So it's miles per hour. Negative 565.68 miles per hour. Now the answer is negative, which means that the distance between the ground and the radar station is shrinking, right? All right, did that help going through everything like that? Make a lot more sense? Okay, I'm gonna give you another one. Y'all ready for another one? Well, I'll put it back up there. Just give me a second. There we go. Let's take 5 minutes. Maybe 4 minutes. It is not the same problem. Read it. Did that help?
Caught me off guard, I'll be honest.
All right, let's go. All right, so who's like completely stuck here? We'll go with someone new. Justin, do you feel better about this one a little bit?
Yes, I do.
Someone who feels like they're kind of stuck. Everyone feels good about it.
No, but I'm not, I guess I'll go. I'm not really super stuck, but I'm sort of stuck. So for my instant picture, I've got a right triangle, but it's going the opposite way. Got 6 for my hypotenuse, 2 for my vertical line. And you're trying to find the angle opposite, the angle basically as the rate of change of that angle
What angle?
Not- of the, what's going to be the sine or the cosecant because it's opposite. You're going for that little opposite of the right angle. I forget how to actually describe that, but
So like right here?
yeah,
This
that
angle?
there. Yeah.
Okay, now Cody drew it the other way around. So this is fine, but I feel like everyone else did it the other way. So we'll get the same answer. Okay, we're gonna get the same answer, but I'm gonna draw it the other way around because it doesn't change anything in the problem as far as the answer. I'm just gonna do it to be consistent with our last picture. This is 2. This is 6. And you said you're interested in this angle, right?
Yes, sir.
Okay, so let's draw the general picture.
So
Here's
you're gonna
this,
be
2.
same thing. And it's gonna be
This is
basically,
not 6, right? This is not
Yeah.
6.
you need
Can we
a
call it X
variable.
again?
Yeah, we can call that X and then we can just call the bottom R again. Well, we can call the angle, the angle R, but
Why don't we call the angle theta?
fair enough. That's probably a good idea.
Now, you don't need X and R. I'm putting X here because we know that at the moment we're talking about X is 6, right?
Mhm.
We may or may not need R, but you told me to put R, so let's just put it. Do y'all like this picture? You want to talk about what you're given or what you want here?
Well, we want the derivative of theta in respect to X, I would think,
With respect to time.
or time. Yeah, sorry.
We do want d theta dt. We want to know how fast the angle is changing with respect to time. I agree with that. At what moment?
At the time that X equals 6.
Moment that X equals 6. So that hasn't changed. What are we given?
The
We're
speed of
given
600 miles per hour.
What is 600?
That's dx dt.
Well, X is the distance from here to here.
DRDT.
dr dt.
Still dr dt, just like the last problem. It's still dr dt. So we did need the r, didn't we? And I'm going to say negative 600 again because it's shrinking.
Mhm.
Do y'all see this is the exact same setup as the last one, with the exception that we have a theta in our picture now, and we want to know how fast that's changing.
Right.
Questions on the setup?
No, just so for the equation, I was thinking we use something like a trig function, obviously, but we're given hypotenuse in the opposite. So
Well, hold on, Cody. When you're looking for the equation, you're always trying to figure out any equation that relates those two variables together. So just any equation you can think of off this general picture that would relate that and that together. You can't use Pythagorean here because Pythagorean is going to be r squared plus 2 squared is x squared. That doesn't have theta in it, right?
no.
But you were saying something about trig functions.
Right. Well, so if we're going to use theta and R, that's going to be adjacent. So it'd be either cosine or cosecant or tangent, I guess.
Okay, so let's see. If we did tangent, what would you be able to tell me about this triangle? What would it be?
Would be its tangent's opposite over adjacent. So it'd be 2 over R. Tangent of
Okay.
theta is 2 over R.
is 2 over r. Does everyone agree with that equation? Does that equation have the two variables that we're interested in connected together? Yes, right? That's all we need. That's all we need. We just need to differentiate it now. So the differentiation might be a little tricky on this, so I'm going to help you out just a little bit. I'm going to rewrite the right side, 2r to the -1. So I brought the r back up to the top and wrote it as r to the -1. I did that so I can use the power rule when I differentiate. You could have also multiplied both sides by r and had r tangent theta equals 2. And then you would have had to have done a product rule. Maybe I'll do that after we finish this, but let's do it. I think we can differentiate. Go ahead, Cody, you tell me, what is the derivative of this equation with respect to time? So start with the left-hand side.
So you're gonna get the derivative of tangent of theta is gonna be secant squared theta is equal to negative.
Hold on. That's right, times chain rule. You took the derivative of the tangent thing.
Oh, times 2. Okay, times, this would be 1.
Oh, no,
No, wait. Oh, this times.
taking derivative of theta with respect to time.
Oh, yeah, just be d theta over dt.
D theta dt. Look, everyone, that's a critical point right there. The derivative of tangent of something, right? The derivative of tangent of something is secant squared of that something. But then chain rule says, now go take derivative of what's in here. What's derivative of theta with respect to time? D theta dt. You need that, right? You need that because that's what you're looking for, right? If you forget that step, then what you're looking for is never going to show up. I was watching a YouTube video the other night. I couldn't go to sleep. And I was looking at a YouTube about implicit differentiation done by this girl. And I didn't like her explanation because it's not the way a pure mathematician would look at it. But if you don't, I guess it's kind of like the easy way. If you're ever taking the derivative of something, like tangent of theta or tangent of m or tangent of q or whatever it is, take the derivative like you normally would, secant squared theta. And just remember that you always have to multiply by d, whatever the variable is over which you're going with respect to. You're always going to have that pop out. It just always does. Now, she doesn't explain why. She just says, we always have to do that. That's why I didn't like the video. But it's the chain rule, right? It's the chain rule happening there. But if you don't want to think about it, just be like, oh, okay, well, I'm always going to have that thing pop out at the end. Let's keep going. Equals, right-hand side, Cody.
It's gonna be -2r to the -2.
Okay, so the 2 stays, comes for the ride, then you brought a -1 out. Now, I realize you put those together already, but I'm not going to yet. So there your -1 came out. Then what? R to the
-2, well, -1 minus 1, so -2.
2, okay?
Times dr dt.
Times dr dt. Chain rule, right?
Mhm.
I'm going to clean this up. Secant squared theta times d theta dt equals -2 over r squared times dr dt. So all I did there is I put the -1 and 2 together, and then r to the -2, I dropped it back down as an r squared.
And then we would have to just divide the whole thing by secant squared of theta, and
Hold on. It's not letting me select this for some reason. That's right. No, it's not going to work. I don't know why it's not letting me select that. Okay, so let's look at this and let's see what we have and what we don't have. All right. It's really weird. It was letting me do it before. All right, so we have secant squared theta times d theta dt equals -2 over r squared dr dt. All right, Cody. So we've got, let's see, secant of theta. Do we know what theta is, Cody?
no, I thought we were trying to figure that out.
Okay, so you're allowed to look at this picture now, Cody. This picture right here, you're allowed to look at it.
Mhm.
Okay, so theta's here, right?
Right.
So you can actually tell me something about theta.
Yeah, we could use the not Pythagorean theorem, but a trig function to actually get the value.
How about sine of theta? Sine
Yeah,
of
sine of
theta
theta.
is opposite over hypotenuse, right?
And then
I
you
know that
solve
sine
for
of theta is-
theta, right?
And solve for theta. So how would I solve for theta here? What do we use in
It would
pre-calc?
be
Inverse and sine inverse of theta.
You do the inverse sine on both sides. That gives you theta on this side, and then you get on your calculator. Very, very important here. I would just be safe and make sure you're in radian mode, okay? Make sure you're in radian mode. So inverse sine of 2/6. And I get that theta is 0.339. I'm going to put radians, not degrees. I want to make sure you understand we're in radians there. So that's our angle. So Cody, do we know theta?
Yes, we do.
We do. Okay. Now d theta dt. Happy to see that. That's what we want.
And then we
Do we know the
have
radius? Do we know the radius, Cody, at the time we're talking about?
no, but we can find it with
No, but
Pythagorean
we can
theorem.
find it, right? Back to this picture over here. We know the radius. We could go find it. Didn't we do that earlier in the previous
Yeah,
problem?
it's going to be our
Root 32.
yeah, root 32.
Okay, so please everyone understand that what I did there in blue was the previous problem. I'm just not going to do that step again.
And then we have dr over dt as well,
We
negative
have that.
600.
And drdt, we have that. Okay, so we should be able to plug everything in now and figure this out. Right? We should.
Mhm.
So we're going to go secant squared of 0.339 times d theta dt is what we're solving for, equals -2 over, hey, root 32 squared is going to
Yep.
get rid of the root, times
Right.
dr dt, which is -600. How do you do secant on your calculator?
I think you have to use the second
This
function,
whole
don't you?
side- This whole side of this whole thing right here is really 1 over cosine of 0.339, all of that squared. So secant is 1 over cosine. So I just rewrote it as 1 over cosine. And so I'm going to just do all that on my calculator right now. Any questions while I'm doing this?
Maybe you can reduce the -2 over 32 to -1 over 16, but other than that, I mean, it's just kind of math at this point, isn't it?
Yeah, it's just arithmetic now. So on the right-hand side, I'm getting 37.5. I'm getting 33.36. Anyone else get that? I'll feel better if someone else got that. No? Make sure you're in radian mode on your calculator. 1 over cosine of that squared. 2 times. No one's getting that?
I'm working on it right now.
Alejandro got it?
I got it too.
Okay. Fair, good. What are our units going to be here? Theta t. Theta is measured in. What have we been measuring our angle in?
Radians.
Radians. So this is going to be radians per time.
Per hour.
Hour. That's it. 33.36 radians an hour. So I think a problem like this is actually pretty realistic, because if you think about this from a different perspective, what we're doing here is we're having this plane fly overhead. Let me slow it down. We're having this plane fly overhead, and we're trying to figure out at a specific instant in time how fast the tracking radar is rotating at a specific instant. So look at this red angle right here and just pay attention to how it grows in the beginning versus when the plane gets close. So we have slow growth, right? Slow growth of that angle. As the plane starts to go overhead, watch what happens. Faster growth, and then it slows down again. Maybe if I speed it up, it'll be, okay, let's watch it again. Slow. And then it's speeding up, speeding up, speeding up, whoosh, goes through those angles. So think about if you're like watching a race, right? Like you're on a racetrack and you're standing on the side and you're watching a car go by real fast. When you're seeing it way down the road, your head's not turning very fast. But as a car comes by and gets closer, then it's like, yeah, right? So you have to increase your rotation angle faster, right? When it's close to you. That would be very useful, okay? Knowing like how fast things are rotating, that would be very useful if you were trying to shoot this plane down, right? Right? I mean, like if I have a gun that's tracking this, a radar controlled gun, I would need to know, how do I need to lead that plane at every instant in time? I'd need calculations to be able to put rounds on that plane, but all of that is just geometry and calculus. And that's what's happening, you know, military, our desire and need, the conflict of human beings on this planet has progressed science and technology, right? Would you all agree with that? I mean, most of the modern things we have today are because we just love to kill each other and we can't get along, right? If we all got along, we'd probably still be, you know, out gathering nuts and berries in a field somewhere, but we can't get along. So we have to have borders and stay out of my shit, don't touch my shit, you know? So that progresses technology. So even though this seems like a plane flying overhead is a stupid little problem, I mean, really, there's a lot that you could do with this. Okay. Well, I mean, we could just keep going, right? It's 2:20. So why don't we try one of the problems that I have not done? Okay, let me do one that I haven't done ever before. If I have, I don't remember it. I'll let, no, we can go easy or hard. Let's go hard. Okay, so here's the question. And I don't think I'm going to give you time to look at it. Or I don't know, it's up to you. You want time? I can give you time. You want a minute to look at it?
Maybe like a minute and a half, just to kind of see if we can piece
Yeah,
something
let
together.
me give you like 2 minutes to look at this. And I need to draw a picture because it references a picture here. We have the ground. We have a trolley, which is just like a little thing on wheels here, a little trolley. We'll call that trolley A. Over here, we have another little trolley, trolley B. And then above the ground, well, there's a wall. That wall is 20 feet tall. And these two trolleys are connected with a cable that goes through a pulley over this wall like that. And what I can tell you is that the cable that connects the two together, the total length of this cable is 200 feet. Okay.
Just right off the bat, would it be too like much of an error to just assume then that like my hypotenuse from like the 20-foot wall to trolley A is 100 feet? Like, would it be bad to assume that it's split evenly?
Oh, from here to here is 100?
Yeah.
Well, I mean, it is at some point in time, but it's not always that case. There is a point in time where it would be equal on both sides.
Okay.
Let me give you a minute or two. Take a look at it. I'll go refill my drink. All right, before I go back on video, I just have a few questions maybe for you to think about. If trolley A is moving away from the wall at 3 feet per second, then do you think that trolley B is also moving at 3 feet per second? Or do you think that the speed of trolley B is somehow different than trolley A? What are your initial thoughts on that?
I mean, I want to say maybe it's the same, but then also if you overthink it, get technical about the friction of the pulley, etc., possibly
Okay, well,
slower.
we're not going
But-
to do friction. Just in terms of the geometry, do you think that they would have the same speed? Bree, what do you think? I see you unmuted.
Oh, yeah, no, that's what I would assume. I just assumed it was moving at the same speed.
Yeah, so you might think it is. I put together an animation to show you what's actually happening. So I'm going to play the animation for you. And I want you to notice when I play it, that this dot's going to move away at a constant speed. And I want you to pay attention to what happens to this dot and how fast it's approaching the wall, which is the y-axis. Okay, so let me back this up. Say we start here. Ready? So pay attention to how fast the blue dot moves. I don't know. What do y'all think? Does it seem like they're moving the same speed?
No, it seems like the red starts to actually slow down as the blue accelerates. As the blue angle gets steeper, the red angle extends out further.
I think it looks the same.
It's the same. So this red dot is moving at a constant rate. That is moving constant. Okay. The blue dot, watch what happens right in this region. I don't know. It's hard to tell, isn't it?
It goes faster.
It
Like,
seems like it might, right? Seems like it might. Now, here's the thing. This is the beauty of calculus, is that if we set this problem up correctly, we'll be able to answer the question and there will be no debate, okay? There will be no, hey, but no, I think it's this, and no, we can put it to rest. Are y'all ready to work on it? Okay, so I'm not gonna ask, I don't know if I'm gonna ask people. The 200-foot cable is fixed. This distance from here to here to here is always 200, isn't it? So what I'm going to do is I'm going to look at this as two different sections. I have this section and then I have this section. And what I know is that as the trolley A moves, I'm going to call this distance from here to here, I'm going to call that X, okay? What I'm given in the problem is that dx dt is 3 feet per second. Do y'all understand what I'm doing? Looking at the picture, starting to assign variables. I know that as this trolley moves to the right, it's moving this direction. It's going 3 feet per second. That was given to me. And so I needed to label this something, so I called it X. Now, as X changes, this yellow hypotenuse, right? If we look at this as like a right triangle, this yellow hypotenuse also changes. And so it's not always fixed. So I'm going to call that H for hypotenuse. Now, trolley B is moving towards the wall, isn't it? It's moving towards the wall. And so I'm going to label that distance from here to here. I'm going to call that Y. I don't know why I'm using Y. I'm just going to use Y. So wait a minute. Don't I want to know something about Y?
Yeah, you want dy of dt.
Yeah, I want dy dt. I want dy dt. I want to know how fast this trolley is moving. So in other words, I want to know how fast Y is shrinking at what moment in time.
When it hits the wall.
Okay, and when it hits the wall, can you tell me about any of the variables, what the value of those have to be?
Y would equal 0.
0?
Y would have to be 0.
Or H equals 200.
Or H is 200. Yes, you can look at it that way also. Well, hold on, not 200, careful. This would be, the rope would go over and go back down to the trolley, right?
So 180, you could
180.
take
So
the
H-
20 out.
So you can look at it as this, or if you wanted to, you could say H is 180. Right, does that make sense to everyone? If we move this all the way to where this one hits the wall, then that distance from the trolley up to the thing and then over, that would have to be the 200. So 20 and 180, that'd be 200. We good? We good? Okay, I need a way of connecting Y and X together. I just need to come up with any equation that relates the two, okay?
Could you do
Oh, you know what? I have to take this real quick, this for.
I mean, if you let H set up 180, you could just do Pythagorean to find the X value itself, but
So if I'm getting this right, the 20 feet is part of cable 2.
What was your question?
oh, I was
What?
just thinking out loud.
No, Alejandro.
Sorry.
Oh yeah, I was just saying, was the 20 feet part of the 200-foot cable 2?
No, he was just saying that because whenever Y would equal 0,
Yeah,
it
it's
would
like,
have to be.
you know, right as the trolley hits the wall, that 20 feet isn't counted in the 200 because the cable, it's always going to be 200. So that's why the H would just be 180 because that's just part of that 200. It's basically saying that the trolley is not going to continue until it pulls that trolley against the pulley itself at the top of the 20 foot. It can't. I mean, maybe it can. We don't know the power of the trolleys, but yeah.
Okay, yeah, I was just listening to y'all there. I need an equation that relates X and Y together. Okay, that's what I need. So there's several ways to do this. Here's the way I'm going to do it. And there might be a more efficient way of doing this, but here's the way that I see it. I see two right triangles. And they are not equal right triangles because this is a moving picture, right? We could be looking at it in this scenario right there, right? So these are These are both individually right triangles, but they are not similar. Okay, it's not right in the middle where they're equal. It's not necessarily that. So what I'm going to do is this. If I know that this whole cable is 200, then wouldn't you agree that this section in blue is 200 minus h? So whatever h is, this section would be 200 minus that. Right, so if this was 100, that would be 100. If this is 120, that would be 80. Now, the reason I did that is because now for each of these triangles, the one on the left, I have a Pythagorean identity. I have y squared plus 20 squared equals 200 minus h squared. You'll follow that? That's for this triangle right here. Also, I have for this triangle that x squared plus 20 squared must equal h squared. You following? And then I notice that they both have 20 squared in them. And so watch what I'm going to do. I'm going to say 20 squared equals 200 minus h squared minus y squared. So I'm just bringing the y squared over. On this one, I'm going to do the same thing. 20 squared equals h squared minus x squared. So if this has to be 20 squared and this has to be 20 squared, then don't they have to be equal to one another? You'll agree with that?
Yep.
This is 20 squared, this is 20 squared. So that means that this must equal this. So I'm going to set those two equal to one another. Okay. Do I have an equation that connects x and y together?
Yes.
Yes. There's a problem though. What's the problem?
You also have h as well now?
I also have h. So I know that if I differentiate this with respect to time, I know I'm gonna get a dx dt in there, which I'm happy about. I know I'm gonna get a dy dt, which I'm happy about, but I'm also gonna get a dh dt, which I don't know anything about, right? So I have an additional variable here, h, that I actually don't want in the equation. So you're ready to see how I'm gonna get rid of it? This is gonna be kind of cool. Take this equation and solve it for h. Solve that for h, and what would you get? You just take square root on both sides, right? Now, it would be plus or minus, right? Normally plus or minus, but h is the length, it's the distance from here to here, so I'm only going to look at the positive. Is that all right with everyone? Now I'm going to rewrite this with this plugged in for h. In a second, not yet. I want to do something first because I'm going to do the algebra on this. So I'm going to square this right now, and that means I actually have to do 200 minus h times itself, 200 minus h, and then FOIL, right? That's what I have to do to figure out what this is. When I do that, I get 40,000. That's 200 times 200. Then I get minus 200h, minus 200h, that gives me minus 400h. Then I get a plus h squared. Then I have minus y squared equals h squared minus x squared. The reason I'm doing this right now, and I didn't plug this in yet, is because if I plug this in earlier, it's going to be ugly. Where here, do y'all see I get a cancel? I get a cancellation of the h squared. Do y'all see that cancels on both sides? I can subtract it. So I get this really nice equation. Well, I don't know. It's debatable whether or not this is nice. 40,000 minus 400 times h. Here's what h is. And then minus y squared, and then equals x, negative x squared. There we go. Do we have an equation that relates x and y together? Yes, and there's no h's anymore, right? All right. Time to roll with this. Okay, time to take derivative of this with respect to time. It's not pretty, okay, it's not a pretty equation, but here it is. Okay, so this is my equation. And now I do my implicit. Okay, so my implicit differentiation, I can do, everyone hopefully sees we have 1, 2, 3 terms on the left because there's subtraction between these, so I can differentiate these one by one. The derivative of 40,000 is 0, right? Because it's constant. Okay, this one's going to be the shitty one, okay? The derivative of negative 400 times the square root of all that, I have to do chain rule. The negative 400 comes for the ride. Okay, times, what is the derivative of the square root of something?
1/2 square root of that something.
Okay, 1/2 square roots of that something. Let me just square the 20 already. Okay, I've been holding off on it, 400. Okay, that's 20 squared. So the derivative of the square root of something is 1/2 times the square root of that something times, don't forget chain rule. Now you need to take derivative of what was in here.
2x.
Carefully take the derivative of that. What is the derivative of x squared?
2x
2x
times dx over
times dx
and then
dt.
yeah, dt over time.
So the derivative of x squared is 2x, but then you have to do the chain rule. Derivative of x is dx dt, not 1. And then plus derivative of 20 squared, but 20 squared is 400, so derivative of 400 is 0. So that's it, right? That's a derivative of this. Minus derivative of y squared.
Minus 2y dy dt.
dy dt equals derivative of right side.
Yeah, negative 2x times dx dt.
There it is. I'm happy. I've never worked this problem out. I knew that the geometry would be tricky. Obviously, this is a lot different than the good old area problem from the first problem, right? I mean, it's not, the formula is not as easy, right? But if we can make the connection, if we can relate the variables, then we can relate the rates, and that's what this is all about.
So I have a question. Well,
Yes.
So is this like a type of question we would kind of get, or like on an exam, or does it get harder?
I think that this would be a more difficult problem. This would be one of the higher level ones. So what I normally like to do on the next exam is what I'll do is I'll give you like 3 related rate problems. And let's say that problem's worth, normally that problem's worth a lot of points. So let's say that your related rate problem on your test is worth, let's say, 25 points on the test. Okay, then if I give you 3 choices, A, B, and C, if you do A, then the highest you can get on it is an 18 out of 25. If you do problem B, then you can get like, 22 out of 25. And if you do C, then you can get the 25 out of 25. In other words, there's kind of like a C level problem, a B level problem, and an A level problem. If you do the C level problem, you get it right, then okay, you get it right, but you can't possibly get the highest score on the test. Does that make sense? It still allows you to do the problem, but if you do the easier one, then you can't possibly be like an A student. Does that make sense? An A student should be able to do the harder problem. That's the way I normally do it. So to me, this would be an A level problem. This problem right here, because there's a lot going on here. Okay, let's finish it up, okay? Because there's still a lot of work to do. Let's look at what we have here. Well, you know what I never drew? I never drew the picture of the situation at the instant. Maybe I should do that. The instant in time. At the instant in time, we have the wall. We have trolley B is here. And we have trolley A is here. We know that this is 180. We know that this is 20, right? Like this. So H was 180 and Y was 0. Remember that? Go with me? The ground. Okay, so let's look at my implicit equation and see what we need. I see right away we're going to need to know what x is, right? Several places in the problem. Do we know what x is? What was x? X was the distance from the wall to the cart, right?
We can figure it out with
You can
Pythagorean.
figure it out, right? Because this from here to here is x. And we know that at this situation, we have 20 here and we have 180 here. So we know x squared plus 20 squared equals 180 squared. And if we solve that for x, I think I did this some point in my life. You know what? I think I did it on the program. I had it figure out what's happening at the instant in time. It was 178.885. 178.885 feet. So I'll know what x is, right? I'm also going to need to know what y is, right? What y is. Do we know what y is?
0.
0. So yeah, we're okay with that. And what else? dx dt. I need to know what that is. Do we know dx dt?
3 feet.
Yeah,
3. Okay. And then dy dt, what?
Is
That's
what we're
what we're solving
solving
for.
Is right here, right? Now, do y'all see we have a problem?
Yeah, you said your y to 0 and it's gonna destroy your dy over dt.
Does everybody see that? Does everybody see that because when the cart hits the wall, right? Y is 0 in our implicit equation. This is 0 is going to kill off dy dt, which is what we are looking for, right?
Mhm.
That's what we're looking for. So here's what we're going to do. We are going to, in order for this to work at all, for us to figure out what's happening right when it hits the wall, do you all agree that we're going to need to somehow make y some positive value? It's going to have to be something, even if it's like 0.00000001. Okay, doesn't matter. It just needs to be positive. Are y'all okay with that?
Mhm.
Okay. So when we say 0 here on this, I'm just going to say very, very, very small. Okay, so now it would just be plugging numbers in. So I'm gonna replace this with 3, this with 3, replace this with 178.885. I'm gonna do that everywhere. I'm trying to do it on my calculator. This might take me a minute. You know what? Let's take our break. Let's take a 10-minute break. And during the break, I'll do this calculation. Okay? Let's do that. We'll come back at 2:58.
Hey, so I have a question.
Yes.
So couldn't we have used the 1/2 base times height one as well
For what?
for the equation to relate x and y? Couldn't we have done 1/2 base times height And then the for base, we just do y plus x instead of b.
So you're saying 1/2 base times height. What is that equal to though?
The area.
The area.
And then we
Okay.
could have, yeah. And then base would just be y plus x.
Okay, and then the height would be 20. Okay,
Yeah.
but what's the area?
Well, we could solve it the same way we solved for x with like, so y is going to be equal to 0. So we could have solved the area
okay.
for at the end.
But the problem with that is you can't fix y to be anything if you're going to set up your equation to differentiate. So we could do that, yes, at a specific moment in time, but we would need our equation to be something where nothing is fixed.
Gotcha.
Make sense?
Yeah, that makes sense now.
Okay, good. Yeah, now I'm not saying that there's not another formula out there that we could have done. There's something, I'm thinking like law of cosines maybe, because you have 3 sides of a triangle. You know, there's different things that we could maybe use, but I just went with what the first thing I saw. So.
Okay. Yeah, thank you.
like straight up just.
Hey, everyone. We ready to get back to this? This problem is actually turning out to be pretty interesting. So what made this problem somewhat unique, first I made up the problem, right? I mean, I've seen these cable problems before, but the moment that I asked you about, right? The moment, what will the speed be when it hits the wall? That's something that I've never seen asked in a question like this. What I've seen is, you know, what's the speed of trolley B maybe when it's 2 feet from the wall or something like that. And so they give you a nice number for Y, which we would be able to compute, right? Do y'all agree that if we knew what Y was, like other than 0, it would be okay here? We wouldn't kill off the dy dt?
Right.
So what I did, okay, is I took this expression. Let me show you something. This is actually very profound. It's a deep idea here. If I take that equation, okay, there's the equation that we were working on. We know what we could do is solve it for dy dt. Okay, so what I did in this first line was I put the -400, I canceled these 2's, and then I put the -400 on top with this x, that's this. Here's the dx dt. I moved all of this to the left, which put it here, and moved all this to the right, which put it over here. Then I divided everything here by 2y, and that gave me an expression for dy dt. Now, here's the profound thing. That's all just algebra. Here's the profound idea. When trolley B is approaching the wall, right? What is Y approaching? 0, right? 0. Now, what is X approaching? As the trolley approaches the wall, what is X approaching? We said it was, what, about 178.8 something? Agreed? Because you would have to have, you know, 20 here and 180 here. So that means that the furthest we could go with X, there's a fixed number that it can go to. You all understand that? So think about this. If dy dt is the speed of that B, what's happening as X gets closer to 178.885? What's happening to dy dt? Well, we know that Y is approaching 0, right? So look at this expression. X, everything I highlight in blue is approaching a fixed number, right? Everything in green is 3 because that's the speed of the trolley A. So do you agree that the numerator is headed to a fixed number?
Yes, and isn't the Y, as it gets closer to 0, it's going to be closer and closer to vertical, so it'd be approaching infinity?
So the Y is approaching 0, right? So we have something that's happening where we have a fixed number over 0, and what does that head to?
Infinity.
Infinity. Which means that the speed of the trolley B is speeding up as it gets closer to the wall. It's getting faster and faster. Now, if you don't believe that, during our break, I actually did this. No, not that one. This one here. I redid my code here a little bit. And what I've done here is I've included in this y equals, so this is going to give you the y value here, how far away y is the trolley B from the wall. And then this is calculating the speed. So this is calculating dy dt right here for us. Okay, so I want you to watch what happens as we start moving. Okay, so notice that initially the speed of trolley B is 0, okay, at the very beginning. Now trolley A starts moving. Now watch what happens to the speed of trolley B. Let me just start moving it. Okay, start speeding up, right? This is the speed I'm looking at, 0.057, but watch what happens. Now remember, trolley A is moving at 3 feet per second. And look, when we get to this point right here, trolley B is already going faster than that. Now it's up at 6 feet per second. 7. Now right here is the interesting part. Watch what happens as I get closer and closer. Look at the speed, 9.5. I may not be going fast enough there. You get closer. We're at 14, 15. You can't even tell I'm moving it, but I am. I might have to go a little bit. There we go, right there. Look, the speed of it is 20 when we're right there. But as I get closer, 21, 25, 30, 50, 100, 6,000. You see that? It's becoming asymptotically fast as we get to the wall. So it is speeding up. Now, is it going to hit the wall at infinity?
No.
No, it's not. I mean, it's speeding up, right? It's speeding up. But in the physical world, you're going to start to have issues with the pulleys, right? I mean, you're going to have this vertical force. All your forces, at the end, all your forces are vertical, right? There's no more forces horizontally. So the main idea here is that it's speeding up. And we can get that from the fact that this derivative, dy dt, heads to 0 in the denominator while the numerator heads to a fixed number. Interesting problem. That would be a beyond a problem. But actually, you know what? If I told you, if I would just change one thing in this problem, then this would be a problem that could go on a test as the harder problem. And that's, if I cross this out and I said, then what speed will the trolley hit the, if I said, you know, what is the speed of trolley B when it is 1 foot from the wall? Then you could answer the question. All right, we need to do another problem, okay? That one turned out to be fun. For me, I don't know if it's fun for you. Let's do another classic problem. This one right here. The Conical Cup Problem. So when I say classic problem, it's like, you know, any Cal 1 student's going to see this. Most Cal 1 students are going to see this problem. All right, I'll let you have a minute to think about it. 2 minutes to maybe just get a couple of pictures drawn or something. All right, let's play ball here. So I'm going to do this a little different in terms of, I'm not going to bring up that sheet. I'm just going to write down instant, general, what I'm given, what I want, the equation, the implicit. All right. I feel like Marissa wants to play. Marissa, you feel like going for this?
Sure. I'm still
Okay.
writing down the question though.
Oh, okay. Have you had a chance to do anything with it or no?
No, I was still writing it down.
Okay. Let's see. Let's go with someone else. How about Gabriella? Feel like, did you get anywhere?
Well, I wrote down the equation for the volume.
Okay, so you found the equation for the volume of a cone?
Yes, sir.
Yes. Here, tell me what you got. I'll jot it down here in the corner. We may need that.
I have pi times r squared times h over 3.
That is the volume of a cone. That is correct. If you have a cone, has a radius and a height, oh man, that's terrible.
So
The
because
volume-
it said it was 6 inches wide, I just put it as the radius equals 3.
Okay, yeah, so let's draw a picture. Let's draw the instant picture, Gabriella. So we have the cone, right, which is the cup, like this. We know that this cup, and it's not drawn to scale, we know that this cup is 4 inches tall, and we know that it's 6 inches wide. Do you agree?
Yes, sir.
Okay. Now we have water that's being poured into the cup. So there's water being poured in here, and they want to know how fast the water level is rising when exactly the moment that the water is 1 inch from the top of the cup, right? So we have to draw the water within the cup like this, right? This is our water in here. And that's 1 inch from the top. Do you agree with that, Gabriella?
Yes, Professor.
Now, go
so
ahead.
is
Do you have
that
a question?
What we're looking for would be dH over dt, right? How fast is the water level rising? That's the rate
Okay.
of the height.
Okay, so you want to know dH dt. I agree. I'm sorry, you want that. dH dt. You want to know how fast the height is changing. But Gabriella, that means in your picture, you need to have the variable h somewhere. Okay, so in your picture, this is super critical. The cup is not changing, right? This is 4. This is 6. But in general, we'll have a water level in here, and that is the h. Agreed?
Mm-hmm.
The h is not 4. Everyone understand that? H is not 4. We're talking about the water within the cup. So h is the level of the water. I agree. We want dH dt. Very good. Now, what are you given, Gabriella?
Would h be 3 since it's 1 inch below the cup?
At that moment, yes. At the moment that h is equal to 3. I agree with that. Because the original cup is 4 inches tall. The water level at the instant we're talking about is 1 inch from the top, which means that h is going to be 3. Very good. So we want to know, how fast is the water level h changing with respect to time when at exactly the moment that h is 3. Good. What about what you're given? Are you given a derivative, a rate of change of something, Gabrielle?
Water is being poured into the cup at a constant rate of 2 pi cubic inches a second.
Cubic inches, right?
But I wasn't sure what variable that would be. I get it, it's over dt, but I don't know if it was dv.
Okay, so yeah, so dv, right? Volume.
Okay.
2 cubic inches per second is a volume. You know it's a volume because, well, it's being poured in, so that's how much you have in there. Cubic inches tells you that it's a cubic measurement. That means it's a volume measurement. So This is the change in volume over time, and that is 2 pi cubic inches every second. Gabriella, is that making sense?
Yes, sir.
Good, you're doing good. All right. Gabriella, you need to somehow try and connect the volume. Now listen to what I say, everyone. Gabriella is trying to connect the volume of the water to the height of the water, not the volume of the cup, the volume of the water to the height of the water. And you gave me an equation, didn't you? Or someone
Yes,
did.
you did. Yeah,
What
it
was
was
the equation?
pi times r squared h over 3 times h over 3.
Now I'm going to write that a different way because we're in calculus now. So anytime we have something like that, it's better just pull the 3 off the bottom and write it this way. 1/3 pi r squared h. Okay, so Gabriella, I agree with that. This is an equation. I'm going to take the middle part out. I don't like that. Gabriella, this is an equation that connects h and v together. Yes?
Yes.
But what other variable do you have in there?
R.
R. And do you know anything? So Gabriella, when you take the derivative of this, you're going to get a dv dt, right?
Mhm.
You're going to get a dh dt. But because you have an r in there, you're also going to get dr dt. And you don't know anything about dr dt, do you?
No, not yet.
No. So we have to eliminate the r from the equation. Just like I did in the previous problem. I eliminated that h. I need to eliminate the r. So now here's the tricky part. How do we get r out of here? Anybody have any ideas?
You get the radius from the general.
So where is the radius on the general? Where is the radius of the water, picture-wise? That's from here to here, right?
Yes.
That's the r we're talking about?
Yes.
Okay. I need a way to eliminate the r from here. Somehow this r needs to go away, and everything that's left needs to be v's and h's.
Square root the 6. Oh wait, no.
Okay, so so be careful here. This radius is the radius of the water, not the radius of the cup.
Got it.
So we can't fix it. Look, so if you've never seen this before, never seen a problem like this, that's why we do it, okay? So you can see how to attack this. Watch what I'm gonna do. Imagine that I had the ability to cut the cone in half, slice it right down the middle, open it up and look at a cross section of it. So imagine that I'm gonna cut now, and also imagine that the water doesn't pour out, okay? So I'm cutting it in half and I'm gonna look at a cross section. If I look at the cross section, here's what I'll see. I'll see a triangle like this, where this is 6 and this is 4. I will also see a smaller triangle in here, right, which is the water level. And I know that halfway from here to here is r, and the distance from here to here is h, right, straight down. This. You'll see what I'm doing? Wouldn't that be what a cross section looks like of that cone? Now here's where you have to put something together. If you were to continue a line straight up, like this, and then just focus all of your attention on just half of this. Let me draw you what we would have. We would have this bigger triangle like this, where this would be 3 and that would be 4. It would be a right triangle. That's this, okay? And then we would have a smaller triangle in here like this. That'd be a right triangle where this would be R and this would be H. Do y'all see that? And if I separate the two, three and 4, and then the smaller one, R and H, what can you tell me about these two triangles? They're what we call
Similar.
similar triangles. Similar because they both have this same angle down here. Whatever that angle is down here, they both have that same angle. And they both have a 90-degree angle, which means that the other remaining angle has to be the same also. So they are similar triangles. And similar triangles are proportional, meaning if I take any two corresponding sides and create a fraction, it's equal to the same corresponding sides on the other triangle. Like, what do I mean? I mean, if I take 3 and divide it by 4, that will always be equal to this one divided by this one, R over H. Now, there's a bunch of ways you could do this, okay? You could also have done the 3 over R is equal to the 4 over the H. Or you could do the H over 4 is equal to the R over 3. You can do it any way you want. It doesn't matter with, well, not any way. You can't do R over 4 is equal to 3 over H. It has to be corresponding sides. So small side, you could do small side over big side on the big triangle equals small side over big side on the small triangle, or you could do small side over small side equals big side over big side, or any other combination. But the key is that we get a proportion. And with this proportion, I can solve this for R, can't I? Why don't I just multiply both sides of that equation by H? If I multiply H here and H here, I get 3/4 H equals R. And now I have an expression for R that I can replace that R with 3/4 H. So I'm going to go back over to this equation that Gabriella had given us. Volume equals 1/3 pi. Now, instead of R squared, I'm going to put 3/4 H squared times H. Are there questions? Do you feel dizzy yet? Is this overwhelming? What's going on?
It's a little overwhelming right now
Yeah.
with everything kind of just sitting here for these couple hours, but not completely lost, so that's good.
Okay, good. I'm going to continue with the algebra on this. 9/16 H squared times H. I just went ahead and squared this. And that means volume equals, I can simplify. We should get 3/16 pi H cubed. And this, everybody, is our equation. For this particular cone, it only works for this cup. We do a different shaped cup, then our ratios change, our proportions change, and we have a different formula. But for this cup, I can tell you that the volume of the water is always 3/16 pi times the height of the water cubed. And now if I differentiate this, I will only get dV dt and dH dt in it, which is what I wanted. Questions?
Where'd you get the H again when you multiplied R over H?
I was trying to clear the fraction. I was trying to solve for R. So I was trying to get R by itself. So I multiplied H on both sides to clear it on this side.
All
Is
right.
that what you're referring to?
Yes, sir.
Okay. Yeah, I wasn't using that one.
So you're saying we would just differentiate that 3/16 pi H cubed, and it would be 3/16 pi that times 2H squared times dH over dt?
Yep, I'm differentiating right now. So derivative of v with respect to t is dv dt. 3/16 pi is a constant. Derivative of h cubed is 3h squared times dh dt, chain rule. And now everything here, you should be able to get. Let's see. Kind of out of room. I'm gonna move this up. I don't know where I can put it. I'll put it right here. Maybe I can make it barely fits in there. So here's where I am. dv dt, I have it, right? Check. H at the moment in time, I do have that. It was 3. And dh dt is what I'm looking for. So this just becomes 2 pi equals 3/16 pi times 3 times h, which was 3 squared dh dt. I get rid of my pi's. I can divide both sides by pi. So I'm getting something like 2 equals, let's see, 3 squared is 9 times 3 is 27 times 3 is 81. So 81 over 16 times dh dt. And then I'll just multiply both sides by 16 over 81. I'm expecting you could do that. If you have trouble with that, then you can talk to me after class, but 0.395 inches per second is dh dt.
The inches aren't cubed, right?
No, and the reason I know that is because when I see h here, dh over dt, h is the height. And so I just ask myself, how would I measure the height of something?
Okay.
Well, inches, right? Not square inches or cubed. It's just inches. And then I divide that by t, which is the time, and time here is measured in seconds, right? It was seconds? Seconds, yeah. So I didn't show you the animation for this one, but here's what it looks like. If we have a cone and we're filling it at a constant rate, then what happens is in the beginning, because of the shape of the cup, in the beginning, it should fill up fast. And then because it spreads out, it should go slower as time goes on. So here it is. So imagine I'm pouring liquid into this. So see how slow it's growing? At the end, it's not coming up that fast. It's actually really slow, but it's going to cycle back. When it starts over, watch how quick it starts growing at the very beginning. See how fast it came up in the beginning? That's because of the shape of the cup.
I was going to say it's narrow at the bottom, so there's less space for it to fill as it gets, or more space progressively as it gets.
That's right, which means that the rate at which we were trying to figure out how fast the level was coming up at a certain point in time, that's going to depend on where you are. Like if you're way down at the bottom, it's coming up real fast, but if you're at the top, it's not coming up as fast. You know, an application of this would be, let's say you have a lake and you have a lot of water coming into the lake and you have a dam and the water level's rising, right? You can somehow try and figure out, like at the moment that it breaches the dam, how fast is the water level coming up, right? So you want to know, like, at what volume that water is going to be coming over the dam. Things like that. These are just all related rate sort of problems.
I did have a question.
Yeah.
So like, I imagine there's probably a yes, but like with like, for example, a lake where it's very irregular in shape and all that, is there really a nice way to put together an accurate equation for that lake, or is it always just going to be?
It would depend on whether or not you had mapped it properly using like sonar or something, and you could get a pretty rough estimate.
Okay.
Yeah, I mean, if it's not a cone, yeah, obviously you can't use the cone equation, but if it's some other shape, you should be able to. The question would become, how do you figure out the volume of something so irregular?
Yeah, that's what I was wondering, is like, if it's not kind of an actual set geometric shape of any kind, I mean, it's going to be.
You can do it with calculus. That's covered in Cal 3, where you're finding volumes under generic surfaces. So if you just have like some generic, just imagine it's like a blanket or something. Imagine you just had some weird, just some weird sort of like blanket shape that has like little hills and valleys in it, you know?
Yeah.
I always think of like if you had a blanket and you were like waving it out in the wind and it's all over the place and you just freeze it, right? And then imagine whatever that is, just imagine going and taking the corners straight to the ground and, you know, projecting onto the ground and then trying to find the volume of that solid. You can do that in Cal 3.
And it's just approximate as close as possible.
It's an exact answer.
Oh, it's exact.
It requires the limit though, of course.
Okay.
Yeah. So it really just goes down to the idea that in Cal 2, what you learn is that if you have an arbitrary function between 2 points, in Cal 2, you will learn that there is a way to find the exact area underneath that graph, exact area. No matter how crazy the shape is, you can find the exact area. And to do it, you actually need to be able to find the antiderivative of a function, which is basically the opposite of the derivative.
So it's like an inverse almost, but maybe
It's almost like an inverse. It's like, we all know the derivative of x squared is 2x, right? So if I ask you, what's the antiderivative of this, you would say x squared, right? So in order to figure out this area under here, you would have to take whatever this function is and tell me its antiderivative. And from that, if you could do that, then we'll be able to figure out the area. But we will cover that at the end of this class. Okay, at the very end, we'll get into the very basic idea of this.
Okay. I'm just assuming it's going to have to be continuous. And I think you said it has to pass a vertical line test. And if it's got an antiderivative, it's got to have a regular derivative, right?
Yeah, so when we talk about functions that you can do this with, we call them integrable functions. So you don't even need differentiability, because like if you take like the absolute value function, it fails to be differentiable at this corner.
Right.
But you can still find the volume, the area under that, even though it's not differentiable at that point. So this function is not differentiable everywhere, but it is integrable.
So it's just got to pass the vertical line test.
Vertical line test, yeah.
Okay.
And there's some other conditions, but
we'll get into it, I'm assuming.
Yeah. Okay, so where the hell are we?
Sorry.
No, it's okay. Okay, those were all relevant questions. All right, so look, there's just no way I could sit here and do enough problems to show you everything. I told you that when we started out. So here's what I'm gonna do. You're gonna have a quiz for the week. I'm gonna send it to you. I'll send it to you after class today. It's gonna be made up of a few different problems from my lectures that I'm going to have you attempt, okay? And I'm not sure how I'm gonna do it yet, but I'll probably give you like 3 problems and ask you to do 2 of the 3 as a quiz. And you know what? You're just gonna try and do the best you can, all right?
We'll be due like by next Tuesday, like the last
I
quiz
think
was.
I think next Tuesday is fair. Yeah, it'll give you something to work on over the weekend.
All right, I'm glad you're putting it Tuesday.
So look for that either later today or tomorrow for me to send that out to you. Okay.
It'll be a Dropbox link as well with I guess the attached problems.
What's that?
I said you'll have it's the Dropbox link again with just an attached Word doc or something like that with problems.
Yeah, I'll have a place that you can send your work.
Okay.
Okay. Unfortunately, I really was wanting to just do these problems all day long, but we can't. We have to move on. So we are moving into the next section. Actually, the next chapter, which is chapter 3. All right. So let me bring it up.
3.1.
All right, so chapter 3 is a weird chapter because it's called inverse functions, all right? Chapter 3, section 1 has to do with exponential functions, which is basically a review from college algebra. So I'm going to cover that today, but I'm going to go extremely fast. All right, so don't be worried about copying this all down. These are all notes you can get on Canvas. 3.2 is inverse functions and logarithms. Again, this is a review from college algebra. I'm going to go quickly. Our main goal is to get to 3.3 and talk about what the derivatives of logs and exponential functions are. Because right now, we have no idea. So let's start with a review of exponential functions. So we're going to quickly go through this, all right? If you feel like you don't remember anything about exponential functions, I suggest you go back and review, all right? I'll try and just point out right here, I'm just trying to point out what are the main things you need to know going into the calculus, right? So hopefully we all remember that an exponential function is a function that looks like f of x equals a to the x. So we have some function where you have a number raised to the power x. Do not confuse this with something like x to the fourth, okay? X to the fourth is not an exponential function because the base is x and the exponent is a number. That's not an exponential function, that's a power function. An exponential function is where you have a number on the bottom and your variable is in the exponent. And when you have that, you have a different sort of graph. And this is what exponential functions generally look like. If the number on the bottom, okay, so if that base there, if that is a positive number, sorry, a number greater than 1, then the graph of this will look like this, and that's called exponential growth. Okay, so examples, 2 to the x would look like this. 3 to the x would look like this. E to the x would look like this. As long as the base is bigger than 1, you're going to have exponential growth. In terms of calculus, we want to understand what these limits are. So see if that limit makes sense to you. The limit as x goes to infinity of this function would be infinity. Meaning that if we go to the right, what is this function, exponential function doing?
Infinitely
It's heading
bigger.
up to infinity, right?
Mm-hmm.
Okay. What if we go to the left? So if we approach negative infinity, what if we go this way? Where's the function headed?
0.
Zero.
Okay. That's what'll happen if your base is bigger than 1. It will always look like that. Okay. What if the base is not bigger than 1? What if it's between 0 and 1, like maybe 1/2 to the x? Well, we get a different picture. Okay. So here's what it looks like if we have a fraction in there like 1/2 or 0.2 or something like that. Then what we get is exponential decay. And so the limits change a little bit. If we go to infinity, the function heads to 0, right? But if we go to negative infinity, the function heads up to infinity. So it's like backwards from what just happened on the previous one. Good? Just a general idea of what happens with exponential functions at the ends. All right, properties of exponents that you should remember. So this is from like almost like pre-algebra. If you have a raised to 2 things being added, it's the same as a to the x times a to the y. So I'll give you an example of this. If I give you like 4 to the 2 plus 3, that's the same as 4 squared times 4 cubed. So if you multiply 2 things that have the same base, you add the exponents together. So this would be 4 to the 5th power. If you have subtraction over there up top, that means you had division. If you take something, raise it to a power, and then raise that whole thing to a power, that's when you multiply the exponents. So an example of this one would be if I had 4 squared cubed, that'd be 4 to the 6th. You're multiplying these two together. And then this property that if you have multiplication, this only works with multiplication. In multiplication between 2 things and you're raising the whole thing to the x, you can just apply the x to both. So an example of this would be like 2 times x to the third. That means 2 to the third times x to the third. These are things you should know already. I'm just reviewing them. Any questions there? Okay, next thing. That's it. We're done with, I mean, there's more obviously with exponential functions, but that's all I'm going to talk about with that.
I was gonna say that section went by way faster this time around.
Yeah. Okay, inverse functions and logarithmic functions. So what you should have learned in college algebra is that a logarithm is just the inverse of an exponential function. So they're inverses of one another. But logarithms, when you graph them, they look like this. Instead of an exponential, they look like this. And so logarithms only exist to the right of the y-axis. Okay, you are not allowed to ever plug 0 into a log, and you can't plug negatives into a log. And this is what the graphs look like. So this is the graph of a log. If the base is bigger than 1, this is what the log looks like. So very important that you understand these two limits for a log. If I take the limit as x goes to infinity for a log function, if I move out to the right, the log function gets bigger and bigger and bigger. Now, it doesn't grow as fast as an exponential, but it does grow. So the limit as x goes to infinity of a log function should be infinity. Now, the limit the other direction, you cannot go over here. Okay, you're not allowed to go over here because you can't plug negatives in. But what you can do is you can approach 0 from the right. And if we approach 0 from the right, we can see that the graph drops down towards negative infinity. And so that's what this second limit is saying. Questions on that? What if we change the a to a fraction, like 1/2 or 0.2 or something? Everything here changes, and our picture looks like that instead. So our limits change. As we approach 0 from the right, we go to infinity. And as we approach infinity, we go to negative infinity. So this just keeps on going down and down and down forever. Questions there about the general look of logarithms? Okay. Properties of logs. So you might recall these properties of logs from college algebra when you were asked to condense and expand log expressions. These properties come up all over the place in calculus, in math in general. And they're really, really important. So make sure let's make sure you remember them. If you have a log, doesn't matter what the base is, if you have multiplication of two things within the log, you are allowed to split that into 2 logs with addition between them. That was called, from left to right is called expanding. And if you go from right to left, it's called condensing. Similarly, if you have a single log with division inside the log, 2 things being divided, you can split it into 2 logs with subtraction between them. And then we have the almighty property 3 that says if you have any log and you have x being raised to a power, you can bring the power out front. This is not taking the derivative. This is just a property of logs. You can just put the power out front and leave the x there. So I'll give you an example of this. If I wrote natural log of x to the 4th power, that can be rewritten as 4 times natural log of x. That is a property of logs. That reminds me of a problem that I used to, when I first started teaching, I worked in this little office with a couple other people that were also in graduate school still. And I remember this problem that somebody put up on, we used to have whiteboards and people would put problems up for others to look at. It was this problem, x to the 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 x forever equals 2. So what number, when you raise it to itself, to itself, to itself, to itself, to itself, to itself, forever equals 2? That was the question. So I'll show you a way you can solve this. If I look at everything in yellow as being like some power n, then this is really x to the n equals 2. And then I can take the natural log on both sides of the equation, like that, and use the property of logs to pull the n out in front. That's the property I just showed you. Right? Feel okay with that? And then let's see, hold on. Well, wait a minute. What is n? What is n? N is the stuff in yellow, right?
Yeah, an infinite amount of exponents.
It's x to the x to the x to the x to the x forever, right? That's what n is. But doesn't that have to be, isn't that what the original expression is, including this x? Like having one more x down here doesn't make a difference, does it? So I need all of this to be equal to 2. Right? That was the original equation. So that means this n can be replaced with 2. And then I can push this back up here. I know this seems weird. Push that back up there like that. And then I can take e on both sides. And what does e and natural log do to each other when you compose them like this?
They cancel each other out.
You cancel each other out. So what do we get? We get 2 on the right, and then the left-hand side, we get x squared. And that means x must be the square root of 2.
And since it's logs, we just have a positive, no negative.
Yeah.
Okay.
So we're going to go and basically say the solution to this is this. If you take the square root of 2 and raise it to the square root of 2 and raise it to the square root of 2 and raise it to the square root of 2 and raise it to the square root of 2 and do that forever, that's 2. So that's the solution. It's weird. I just wanted to show you, like, there's that property that I just was covering. That's that property being used to solve a pretty weird looking problem. Okay, back to the notes. Sorry, went off track there. Okay, so these you need to know. All right, these are the properties. These are the properties of inverses. I actually just used this one. When you put natural log and e together, they kill each other off and you just get whatever was up here in the exponent. It doesn't matter if you do the natural log of e or if you do e raised to the natural log of x. Either way, it's going to spit out x. So examples of that would be, like, if you do natural log of e to the 4th, the answer is 4. If you do e to the natural log of 4, it answers 4. Third property, everyone should know. Any number to the 0 is 1, except 0 to the 0, but any number to the 0 is 1. And then natural log of 1 is 0 is something you should know. And the last one, natural log of e is 1, is another one you should know, because this is really just this property here with x being replaced with 1. So if you do natural log of e to the x, your answer should just be x. All right, again, this is stuff you should have seen. Last thing is this thing called a change of base formula. So if you remember from college algebra, when we talk about logarithms, like if I write log base 4 of 10, what this is really asking you is to figure this out. What 4 raised to what power would be 10? That's what this is really saying. Log base 4 of 10 means, hey, 4 raised to what power is 10? That's what it means. Now, we can do this on our calculator, but most calculators don't have a log base 4 button. So we have this very important change of base formula that allows us to convert this into the natural log of 10 over the natural log of 4. Does everyone see that this right here, a is 4, x is 10, and then just apply the formula? And we can do that on our calculators. That's why your calculator only has a natural, well, some of them have more than natural log, but technically you only need the natural log button. If you have that, you can do any log out there. So if I do that on my calculator, I get approximately 1.661. So that means if you take 4 and raise it to the 1.661, you should approximately get 10. All right. Feel good? That's the review. That's all you get. All right. All right. Let's do this. If you don't mind, please give me a moment. Let me go do something real quick. What do we want to do here? Yeah. Okay. Give me just a minute. Okay. So there's one particular function in math that you've studied. We just talked about it, right? This thing is called the natural exponential function. The inverse of this function is ln of x, and that's called the natural log, right? Y'all remember hearing this, yes? College algebra, you learn about this e to the x and its inverse natural log of x. Now, yes. Were you told that it's an important function?
I believe he mentioned it, yes.
Okay. Just so we understand, do we all know what E is? Like, what is E? I mean, it's a letter, obviously, but what does it represent? It's just a number, right?
So isn't it like, it's some kind of constant?
It is a constant. It's approximately 2.718. Kind of like pi, right? Like everyone here seems to be fine with the idea that pi is about 3.1415, right? Like everyone just like, oh, okay, yeah, pi is pi, you know. And then you're told about this specific base, right? this particular base E, that's about 2.718. And that's very special. It's so special, instead of writing 2.718, we just write E. Kind of like pi is so special, instead of writing 3.1415, we write pi. Both of these numbers are irrational. Do you remember me telling you the story about the sky and the stars and the darkness?
Yeah, you
Remember that
can't,
story?
you'll never be able to grab out that exact value out of randomness.
That's right. Pi and E are those darkness, are their darkness numbers, okay? They're irrational. There's an infinitely many of them, but E in particular is just, there's something about E that makes it special, all right? And in college algebra, a lot of times your professor won't tell you what makes it special. So I'm going to tell you now why it's special, right? Why we call it the natural exponential function. And the story goes like this. As mathematicians and as thinking human beings, we asked ourselves a question at some point in time. After Newton developed the calculus and Leibniz developed the calculus, there seemed to be this kind of natural question. The question was this: does there exist a non-trivial function such that the original function is equal to its own derivative? That was the question. Now, let me show you an example of a trivial example. If someone were to say, well, sure, yeah, take the function f of x equals 0. Do you all agree that that is a function? Just constant. If you were to graph it, it would look like this. It's just this really boring function that just goes, it's basically the x-axis, isn't it? Horizontal line. What is the derivative of this function? What is the derivative of 0?
0, you don't have
0,
one.
right? So basically you could tell me, yeah, f of x is equal to its own derivative in this case, isn't it? But this example is trivial. And the reason I say it's trivial, or we say it's trivial, is because that is a boring ass function, right? F of x equals 0 is just 0. Who cares? I mean, no matter what you plug into it, you get 0. Now, would that work for any function that's a constant, like f of x equals 3? Would it work? Well, what's the derivative of that?
It's
1.
0.
It's 0, right? And those aren't equal. So this is a trivial example, but it's like there's not a bunch of trivial examples. This is pretty much it. The question was, is there something non-trivial, some other function that is equal to its own derivative, right? That was the question. And so we went on this hunt looking for a function that did that, looking for this function that behaved that way. Now let's try and appreciate what it would mean. What would this mean if a function was equal to its own derivative? Let's try and understand that visually. Visually, it would mean this. Let's say we had the function, whatever it is, f, okay? It means that if we go to some value x, we would have some y value here, right? Which would be f of x. For the function to be equal to its own derivative would mean that the slope of this tangent line, right, m, the slope of that tangent line at x would have to be equal to the original function's value at x, which means that this y coordinate is actually the same as the slope. Let me say it again. For us to find a function who's equal to its own derivative would mean that we have found a function that if you wanted to know the slope of the tangent line, you simply just have to look at the y value of the function. No other function really, well, we wondered if there was even a function that did this, okay? And it turns out there is, and there's only one. It's unique. And guess which function it is?
E?
F of x equals e to the x. That is the one. That's the one. There's no other function that does this. So since we can't explain why it's the only one, it just kind of naturally is, right? It just naturally is the one. Then we call it the natural exponential function. So in summary, okay, in summary, all you really need to know is this. If f of x equals e to the x, then f prime of x equals itself. And that's it. And that's on your formula sheets. Show you. Remember your derivatives here?
Just a question, sir. When you were talking about the special formula or the special function, I don't know why, but one-to-one function kept popping into my mind. I know that's not right, but I'm just trying to remember what that was exactly again. One-to-one function.
E to the x is a one-to-one function, but there are plenty of other one-to-one functions that don't have this property.
Okay, yeah, I knew that one right. I just couldn't remember. Okay.
Yeah, like x cubed is one-to-one. If you graph x cubed, it's a one-to-one function. But if you take its derivative, it's 3x squared, which is not equal to x cubed. So okay, so it's equal to f of x equals e to the x is its own derivative, and it's the only function that exists that this is the case. Okay, so let's consider something. What is the slope of tangent line, not the equation, just the slope of the tangent line to y equals e to the x at x equals 2? Bree, you look like you want to say.
Oh, at e to the x?
E to the, well, the
Oh.
derivative of it is
Oh,
e to
sorry.
the x, but then at 2.
2
So e squared.
squared, yeah.
Yeah. So the slope of this tangent line would just be e squared. What would the slope of tangent line to y equals e to the x be at -1?
E to the -1.
E to the -1, whatever that is. Okay. It is the only function that behaves this way. I'm going to try and show you something. Normally, I don't show this early in your math life, but I think it would be worth you seeing. It's pretty awesome. So what I'm going to write down here, you have to take on faith first, okay? In other words, I'm going to tell you this is true, and you're either going to like accept it or not. What if I told you that e to the x is actually equal to 1 plus x squared over 2 plus x cubed over 3, 2 times 3, plus x to the 4th over 2 times 3 times 4, plus x to the 5th over 2 times 3 times 4 times 5, plus x to the 6th over 2 times 3 times 4 times 5 times 6. And that continues forever and ever and never stops. What if I told you that was true? Okay. Let's just see. Hold on. How can I do this quickly? No, let's not do that. Okay. You just have to believe this is true. Okay. This is what's known as an infinite series. You study this in Cal 2. All right. So if you take on faith that that's true, I would like to ask you what the derivative of that would be. Okay, so you have a bunch of pluses, right? So let's just start differentiating one by one. What's derivative of 1?
0.
Plus, what's derivative
1.
of x?
1.
Okay, what would happen here? The 2 would come out and it would get killed off, right?
Mm-hmm.
What would you be left with?
Just an x.
Just an x. Okay, here, the 3 would come out So you'd have x squared on top, and then it would cancel with one of the 3's here, and what would you have on the bottom?
2.
2. Okay, plus here the 4 would come out. You had x cubed on top, and then it would cancel with this 4.
So you have 6.
You'd have 2 times 3 again. I'm just going to write it as 2 times 3.
Okay.
Next one, 5 would come out. You'd have x to the 4th. It cancels with that 5, and you'd have 2 times 3 times 4. Let's go one more. 6 comes out. You have x to the 5th over 2 times 3 times 4 times 5. Do y'all recognize this? That is this. It's the same thing.
Yeah, it just pushes it back one spot.
Yeah, the 0 doesn't matter. It's gone. These are exactly the same thing. E to the x, it turns out you learn in Cal 2, that's the definition of e to the x. And you can see from that that it is its own derivative. Kind of crazy. All right, so we all should know now the derivative e to the x is itself. You ready for something harder? Yes, of course you are. So let's try this. Example, if y is equal to e to the x squared plus x, find y prime. All right, so you have to just kind of squint your eyes a little bit and see the chain rule here. You have e raised to something, right? E raised to the green thing. The derivative of e to anything is itself. But then what do you think the chain rule says we need to multiply by?
By x? Or like
By
what?
The x squared plus x.
the x squared plus x. That's the thing that's inside the e function. So we have to multiply by 2x plus 1. And we're not going to get dx dt or anything like that because we're not differentiating. We're going back. This is like before implicit differentiation. It's just traditional derivatives.
The before times.
Yeah, the good old days. Let me give you another one. If y equals x e to the x, find y prime. Okay, so what do y'all see happening here?
Product and chain rule.
Product right there, right? Y'all see that product rule? So the derivative of this should be the derivative of the first one, 1 times the second one, plus what's derivative of e to the x?
E to the x.
E to the x times
X.
x.
So it wouldn't be a chain rule with the e to the x just by itself?
There is a chain rule, but what's the derivative of x?
Oh, 1,
with
right.
respect to x? 1, right?
Right. I just got the dy over dt in my mind.
I know, we're all fixed on the related rates. I understand it's tricky because we're going kind of back now. And this actually could be rewritten as e to the x times 1 plus x. Since they both have an e to the x in them, you could factor it out. If y equals, how about this? E to the sine x. Hold on, e to the sine of x squared. So the derivative of this should be, we have e to something, right? You got e to something, so the derivative of that should be itself. But then chain rule says now you have to multiply times the derivative of what's up here, which would be what?
Cosine 2x.
Cosine, careful, that's a chain rule. So you first take derivative of the sine, right, which would give you cosine of the x squared.
Right. Times 2x.
Times 2x. Understand, Jair?
Yes.
Does everyone understand that? Derivative e to something is itself, then times, then you got to go back to your rules. What if y equals e to the x squared sine x? Well, first, derivative e to anything is itself. Times, now, when we take the derivative of what's up here, what are we going to have to use?
Product.
Product, right? We have a product right there. So that means I need my product rule right here next to this, attached with multiplication. So I'm going to have 2x sine x plus cosine x times x squared. So there's my product rule on this right here. So I'm trying to give you here a couple of different varieties of problems. You know, it's simple enough to say derivative of e to the x is itself. But generally speaking, here's what we really have. If you have y equals e to some junk, right, whatever it is, the derivative of this is going to be e to the junk. You just rewrite it. But then you still have to multiply that times the derivative of whatever that junk is. That's the chain rule. That's probably better for you to kind of burn into your brain. Derivative of e to something is equal to e to something times the derivative of that something, whatever it is. And if that turns out to be product rule or quotient rule or chain rule, whatever it is, you still have to be able to do that. So what we're doing is we're adding this new element. With all the derivatives we've already learned, all the rules, we've added this new function that throws kind of a twist into things. Questions?
I was just curious, where did e like actually come from? Like, I know they were trying to find a function that was, you know, it's a non-trivial representation of that, but I don't know. It's just like, what were they trying to actually solve when they were basically coming up with the concept of e is what I'm not understanding. Like, where was this being? Maybe this is a conversation for office hours.
Well, I mean, I really do think it came from the idea of, is there a function that's rate of change is equal to its value at any point in time?
Okay, I guess then to rephrase, what was the purpose of that? Why were we looking for that?
Oh, okay. So why would you want that? Well, one could just be pure mathematicians like to think that way, first of all, like, oh, I wonder if this exists. But it turns out that a lot of things in the real world behave that way. E shows up in places that we wouldn't expect. I'll just give you a very simple example. You've probably seen this before in finance or in when you talk about interest formulas, simple interest. You remember seeing that in college algebra?
Unfortunately, yes.
Yeah, so that's the shampoo. I call that the shampoo formula because pert is a shampoo. So there it is. There's E. So what's happening here is that, and we haven't looked at this yet. We need to go one or two more sections before we can do it. It turns out that if you remember how in college algebra, the way finance interest works, like let's say you have money and you put it into the bank and then they could give you an interest on that money. Maybe they do that once a year. Then we say it's compounded, you know, annually, just one time. What they can also do is they can take your money and compound it or do the interest twice a year, okay? But they don't give you the full, like let's say it's a 5% interest. They don't give you 5% twice. They give you 2.5 twice. So half of the 5. If you cut it into 4 pieces, they'll compound the interest 4 times, but they won't do the full interest. They'll do the interest divided by 4 each time. So the question is, what if I want to compound your interest continuously? That means compound the interest at every instant in time, all the time, every instant of every moment of every day, right? Then what happens is that the interest, you take the interest and divide it by infinity, and you do it an infinite number of times. And amazingly, when you do that, E appears.
So the E is just really just going to be pretty much any or most like exponential functions of some sort like that are with like time and things.
You're going to have to wait on this, but here's what we're going to learn. That's what E is. E is a limit. It's the limit as n goes to infinity of 1 plus 1 over n to the n.
Okay.
Okay. Which we actually have seen this back with when we were doing, well, you know what, let's just wait. No, we'll see this. We'll see this again. Just so stand by on this, okay? Okay, what are we doing? 15 minutes? All right, so we all know that the derivative, hopefully, the derivative of e to something is itself times the derivative, whatever that something is, all right? Now, what if it's not e though? Because e to the x is a very special exponential function, but what about more generally? What if f of x is just a general exponential function, a to the x? I mean, we know what happens if it's e, because e is a very specific example, but in general, what about a to the x? Well, it turns out that the derivative of this is actually itself, but not exactly. You then have to scale it, multiply it by a number, and the number is the natural log of a. This is on your formula sheet. Right here, here's formula 9, tells you derivative of e to the x is itself. Derivative 10 tells you in general the derivative of a to the x is a to the x times natural log of a. So just know that you have access to that formula if you need it. Now, I'll give you a specific example of this. Let's say that y is equal to 4 to the x. The derivative of that is itself times the natural log of 4. And just remember that natural log of 4 is just a number. So it's kind of like we're saying that the derivative of this is almost itself. We just have to scale it by, excuse me, I feel like I'm going to sneeze. Okay. We're going to scale it by a number. So it's not exactly the same function. They're almost the same. What's cool about this is that what happens when you do e to the x and you use this formula? Use this formula for e to the x, and what would it be? E to the x, natural log of what?
X.
E.
Careful. It's a, whatever the base is, natural log of the base. So the base here is
Natural log of e.
natural log of e. And what is natural log of e? 1. So that means you get e to the x times 1, which is e to the x. So I guess what I'm saying is like this is like the general formula. Okay. So we have now derivative e to something, we know how to do that. Derivative a to something, we can do that, right? This formula right here. The next question is what's the derivative of the log functions, right? So let's get to those. And we'll start again with the most important log, which is the natural log. So if f of x equals natural log of x, then the derivative of it, y'all ready for this? Y'all ready to know what the derivative of natural log of x is? It is.
Is it e to the x?
Nope.
Oh.
It's 1 over x. It's weird. It's 1 over x. More generally speaking, if f of x equals natural log of some junk, then the derivative of that will be 1 over the junk times the derivative of the junk. I'll show you in an example. If y is equal to the natural log of, let's say, sine x, what would the derivative of this be? According to this, if you have natural log of some junk, then the derivative should be 1 over the junk, and then chain rule says times the derivative of the junk.
So it would be 1 over sine times cosine.
1 over sine x times cosine of x.
Can't you then just move that across and then turn that into cotangent?
Yep. So derivative of the natural log of sine of x is actually cotangent of x. What if y equals natural log of x sine x?
It's gonna be 1 over x sine x times. Actually,
So
it'd
1 over
be
junk times, now the
times a-
derivative of the chunk.
One.
gonna be sine of x plus, or it's sine of x.
We'd have product in there, wouldn't we? We have a product
Or
rule
yeah.
right there. So we'd
Yeah.
have to do 1 times sine x
Times
plus
x
cosine x
times x.
And then maybe you put it all together as one, like,
Yeah, you could just turn into x cotan x.
yeah, you could do that, or you could split it into 2. Huh, that's weird. Do y'all follow that answer?
Yes.
If I wanted to, couldn't I do sine x over x sine x plus x cosine x over sine x? I could do this, yes? That's out, oh, x, sorry, I forgot to put the x down here. And that algebraically is just 1 over x plus the x's cancel here, and I just get cotangent x, don't I? I'm just showing you that, yes, this is the answer. But if you algebraically simplify, you get this, right? Now, why did I show you that? Showed you that because, do you remember we were talking about properties of logs? And we said that if you have multiplication in between, you can split it into 2 logs with addition. Didn't we say that earlier? College algebra, multiplication between 2 things inside of a log, split it to 2 logs with addition. Now, if I ask you for the derivative, what's the derivative of natural log of just x? 1 over x, right?
1 over x, yeah.
And then what's the derivative of natural log of sine x? We just did that, didn't we?
It's 1 over sine x plus
Times.
or yeah, no,
cosine
yeah,
x,
times. Yep.
which is cotangent x, right? Same answer. Just showing you that if you would have done the property of logs first, you would have been able to get the same result. Okay. So here's, I think I'm going to call it a day. I think I'm starting to get that feeling that I've come to the end of the road with your, you know what I mean? It's been a long day. Okay.
I'm dragging a little.
Yeah. So here's what I want you to do. I want you to focus all of your attention over the next 2 days when you're doing your homework on the related rates. So don't worry about, oh, by the way, and I'm going to tell you this, for 3-1, 3-2, these homework assignments, you don't have to do those, okay? Those 3-1 and 3-2 are really just reviews of college algebra. So I'm only interested in the homework that's going to go with 3-3. That's the stuff that you're going to be tested on, okay? Don't start that yet. Just wait, all right? Related rates, there's plenty in related rates to fill you with things to do for the next 3 weeks, okay? So do everything you can before we meet again to do those problems there. And in addition to that, to work on the problems that I'm going to send to you, all right? My recommendation would be to try and do some of those first, maybe. I don't know. I mean, it doesn't matter. Each problem's different. So, you know, see how it goes. If you get stuck on the quiz problems, maybe go try and do some homework problems first, or however you want to do it.
So the homework problem, will they have like all kinds of like levels of like, you know, A, B, and C, like you mentioned?
There's a pretty good mix. I don't think any of the homework ones are like really challenging. Like I think the problem, well, you know what, there's some in there that are tricky. It depends. I mean, like you have to be willing to go to any formulas that you've learned, right? So you might be pulling law of sines somewhere. You might be pulling law of cosines in a problem. I mean, just anything that you have used in the past that connects things together with geometry is on the table. So for some people, they'll be like, oh yeah, if I have the triangle, I can do law of cosines. Some people will be like, what, law of what? You know, so it depends on everyone's level for that. Sorry. All right, related rates, homework. See how it goes.
So the quiz will be due by next Tuesday. You
Yeah,
said?
I'll give you a week on it.
If we really run into trouble, can we pop in and ask you for help? I mean, it's a
course.
quiz technically, but
Of course, yeah. I mean, what I would prefer is that you know, try and work it out. If you can't, you know, come to me for help. But if any of you are talking to each other outside of class, I encourage that. I don't mind you helping each other out. What I don't want is you just going and finding someone that knows how to do it, like a tutor, and just, I really need to get 100 on this. That might help you for the quiz. It's not going to help you for the test. So I hope that I kind of illustrated that today when I was going through the problems, that you're capable of learning this. You just have to be willing to like suffer through it a little bit. You'll start to get more comfortable with it. All right. Good luck, everyone. We'll see you in a few days. I'll hang out here if you have any questions.
so